Imagine worlds that defy our understanding of what a planet can be. Beyond our familiar Earth lies a universe filled with planets that could only be described as terrifying. Each one offers a glimpse into extreme environments and conditions that push the limits of life as we know it. From the burning heat of Gliese 581c to the hurricane-force winds of HD 189733b, the cosmos teems with extremes that challenge our beliefs about habitability and survival. When we talk about planets that may be considered scary or dangerous, we are often referring to the extreme conditions that exist on their surfaces or in their atmospheres. These conditions can pose significant challenges for any potential life forms, including those we may recognize, as well as those entirely different from us. Common factors that contribute to this categorization include intense temperatures, hazardous weather, and toxic atmospheric compositions. For example, take Venus, our closest planetary neighbor. It has a thick atmosphere filled with carbon dioxide, and the pressure on its surface is about 90 times that of Earth. To make matters worse, temperatures can soar above 400 degrees Celsius, hot enough to melt lead. Such extreme conditions create an inhospitable environment that would be deadly to humans and unprotected machines alike. Another interesting case is Jupiter, a gas giant that, with its immense size and swirling storms, features the Great Red Spot, a giant storm larger than Earth that has raged for centuries. Its atmosphere is filled with lethal radiation, and its high-pressure zones present a challenge to any spacecraft attempting to explore it. These characteristics render Jupiter not only daunting but potentially dangerous for future explorations. Lastly, we can't overlook the icy bodies of our solar system, such as Europa, a moon of Jupiter. Beneath its frozen surface may lie an ocean of liquid water, one of the key ingredients for life. However, the prospect of navigating through a thick layer of ice presents its own dangers. Overall, whether a planet or moon is deemed scary emerges from its environmental extremes, making it both fascinating and perilous to contemplate. Scientists engage in a fascinating process to uncover and categorize planets, identifying which ones may seem scary or menacing. The term scary often reflects the hostile environments these planets manifest, either through extreme temperatures, violent weather patterns, or toxic atmospheres. Through a combination of remote sensing technologies, mathematical modeling, and spacecraft missions, researchers investigate planets both within our own solar system and beyond. When scientists search for exoplanets or planets outside our solar system, they first look for certain key traits. The characteristics of a planet, such as size, distance from its star, and the type of star itself, play crucial roles in determining whether an environment could be hazardous. For instance, a planet located too close to its star may experience boiling temperatures, while one situated too far could be a frozen wasteland. In this way, some planets are categorized as dangerous simply due to their extreme climates. Moreover, scientists also analyze the atmospheres of these celestial bodies to understand their composition. The presence of harmful gases like sulfuric acid or high levels of radiation suggests potential dangers to any hypothetical life forms. In our own solar system, planets such as Venus, with its crushing atmosphere and intense heat, and Jupiter, with its violent storms and radiation belts, are frequently deemed menacing because of these extreme conditions. Ultimately, while the categorization of planets as scary may come from an anthropocentric perspective, it highlights the diversified nature of planetary environments. This classification not only informs our understanding of those planets, but also enriches our knowledge of potential life elsewhere in the universe. Every new discovery creates pathways to understanding the vastness of space and the diverse worlds that inhabit it. Gliese 581c has earned its nickname as a Goldilocks planet due to its position within the habitable zone of its parent star, Gliese 581. The habitable zone is the region around a star where conditions might be just right for liquid water to exist, a crucial ingredient for life as we know it. This tantalizing possibility sparks the imagination of scientists and enthusiasts alike, as it suggests that Gliese 581c could boast the right temperature for sustaining life, not too hot and not too cold. However, the story of Gliese 581c is not without its complexities. While it sits comfortably in the habitable zone, it is also a large, rocky exoplanet. There's speculation that it may be tidally locked to its star, which means one side perpetually faces Gliese 581 while the other remains in eternal darkness. This can create strikingly different conditions on either side. The sunlit hemisphere could experience temperatures warm enough to support liquid water, while the dark side might be a frozen wasteland, presenting immense challenges for any potential life forms. The atmosphere plays a crucial role in whether life could thrive on Gliese 581c. If it has a substantial atmosphere, the heat from the star might distribute evenly across the planet, allowing for more stable conditions. Conversely, a thin atmosphere may lead to extreme temperatures where life would struggle to survive. So, while Gliese 581c sparkles as a hopeful candidate in the search for extraterrestrial life, the complexities of its environment remind us that the universe can be a balancing act of extremes. The fascination with this planet lies not just in its potential, but in the myriad possibilities that could shape its landscape and the life it may or may not harbor. Gliese 581c, a rocky exoplanet located about 20 light-years from Earth, presents a unique dilemma for potential habitability. Unlike Earth, this planet orbits in its star's habitable zone, where conditions might allow for liquid water to exist. However, this possibility comes with daunting atmospheric challenges that could make life as we know it rather unpredictable and alarming. The primary concern lies in the planet's extreme greenhouse effect. It is theorized that Gliese 581c could possess a thick atmosphere rich in carbon dioxide, which may lead to oppressive heat. The intense pressure and temperature could render the planet much hotter than Earth, potentially creating a steam-rich environment where any liquid water would be constantly evaporating. This unsettling scenario would lead to uninhabitable conditions akin to those found on Venus, a planet often cited as a potential cautionary tale for habitability beyond our homeworld. Moreover, Gliese 581c may experience significant tidal locking because it is close to its host star. This means that one side of the planet is perpetually facing the star, while the opposite side remains in constant darkness. Such a situation could lead to extreme temperatures, with the sunlit side becoming scorchingly hot, while the dark side could plummet into bitter cold. These stark temperature gradients could create violent weather patterns, making it an inhospitable environment for any life forms. As scientists explore the potential for life beyond Earth, the conditions of Gliese 581c serve as a reminder that the search for habitable worlds is complex. While the possibility of liquid water exists, the atmospheric conditions raise serious questions about the planet's ability to support life. The very traits that might make a planet seem promising at first glance can often turn out to be its biggest obstacles in the quest for habitation. The proximity of a planet to its star plays a crucial role in determining its environmental conditions. Take, for instance, Mercury, the closest planet to the Sun. With no substantial atmosphere to trap heat, Mercury experiences extreme temperature fluctuations. During the day, the surface can reach sweltering temperatures of over 800 degrees Fahrenheit. Yet at night, it can plunge to nearly -350 degrees Fahrenheit. This dramatic temperature change highlights how distance from the Sun directly influences a planet's ability to retain heat. In contrast, Venus, often called Earth's twin, holds a different story despite being further from the Sun than Mercury. Venus experiences incredibly high temperatures that can soar to around 900 degrees Fahrenheit, hotter than Mercury. This occurs largely due to a thick atmosphere composed mainly of carbon dioxide, which creates a runaway greenhouse effect. The gases trap heat effectively, resulting in consistent, stifling temperatures across the planet. The differences between these two planets illustrate how distance from a star does not solely dictate temperature extremes. Atmospheric composition plays an equally significant role. Additionally, Earth is uniquely positioned in the so-called Goldilocks zone, where temperatures are just right for liquid water to exist. This ideal spacing allows Earth to sustain a diverse range of climates, from frigid polar regions to tropical paradises. The stable temperatures support complex ecosystems and weather patterns, demonstrating that the distance from our star provides a balanced, nurturing environment unlike that of its neighbors. Understanding how proximity to a star affects environmental extremes on other planets can also give us insights into exoplanets orbiting distant stars. By studying these celestial bodies, scientists speculate on their potential habitability and environmental conditions, which may help us uncover whether life exists elsewhere in the universe. As technology advances, our ability to observe these distant worlds continues to expand, promising exciting discoveries about the cosmic neighborhood around us. Studying distant planets like Gliese 581c presents a unique set of challenges that astronomers have had to navigate. For starters, these exoplanets are located light-years away from Earth, which means that the light we see from them is often faint and comes from great distances. This distance makes it incredibly difficult to gather sufficient data. Most of our knowledge about these distant worlds comes from indirect observations rather than direct imaging. Telescopes must rely on techniques that measure slight changes in light to infer properties about the planet, which can lead to less certainty in findings. Another significant challenge is the presence of the host star, which can overwhelm the signals from the planet itself. In the case of Gliese 581c, the star is much brighter than the planet, making it challenging to detect the faint light reflected from the planet's surface or its atmosphere. This interference requires sophisticated techniques and careful data analysis to differentiate between the light that comes from the star and that which comes from the planet. Astronomers often need to develop methods to minimize this star glare, enhancing their ability to study the planet closely. Additionally, characterizing the atmosphere of these distant planets poses its own hurdles. Although scientists can detect some atmospheric components, they often struggle to determine composition accurately, especially if the atmosphere is thin or if the planet is shrouded by clouds. Understanding the atmospheric pressure, temperature, and chemical makeup is crucial for assessing the potential habitability of exoplanets. Each piece of data adds to a complex puzzle that scientists have yet to fully solve, leading to uncertainties about even the most promising candidates like Gliese 581c. Finally, the limitations in our current technology can restrict the breadth of data we gather. While next-generation telescopes aim to improve our observational capabilities, there are still aspects of exoplanets that remain elusive. Continued advancements in observational techniques and a more refined understanding of planetary systems are necessary for us to piece together the mysteries of these intriguing worlds. Despite these challenges, the quest to understand planets like Gliese 581c drives forward, revealing the vast intricacies of our universe. Tidal locking is a fascinating phenomenon that occurs when a celestial body takes just as long to rotate on its axis as it does to orbit another body. This means one side of the locked body constantly faces the planet it orbits, like how our moon presents only one face to Earth. This can create extreme environmental conditions. For instance, on a tidally locked planet, one side could be scorched by unending sunlight, while the other side is cast into perpetual darkness, resulting in stark temperature contrasts that can vastly affect the atmosphere and climate. On the sunlit side, temperatures can soar to scorching levels, making it nearly impossible for life as we know it to survive. This relentless heat could lead to severe weather patterns, such as hurricanes and superstorms. The constant exposure to heat also affects the surface, where rocks and minerals could be altered beyond recognition, potentially releasing harmful gases into the atmosphere. Conversely, the dark side of a tidally locked planet presents its own terrifying challenges. This area may become frigid and inhospitable, with temperatures possibly plummeting to extremes that might freeze any potential water present. The absence of sunlight would prevent the formation of a stable atmosphere and ecosystems, creating a barren, icy landscape. The harsh conditions could also lead to the accumulation of ice, resulting in the possibility of a thick, unbreathable atmosphere if such a planet trapped gases from volcanic activity. The stark divides created by tidal locking can convey an overwhelming fear of environmental extremes. Life could be forced to adapt in unimaginable ways, or may find it utterly impossible to thrive. Understanding these conditions deepens our comprehension of exoplanets and sparks curiosity about the vast diversity of worlds in our universe, further underscoring the delicate balance required for life to exist. Gliese 581c holds a special place in the search for extraterrestrial life due to its location within the habitable zone of its star system. This zone, often referred to as the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Water is fundamental to life as we know it, making Gliese 581c a prime candidate for further investigation. Discovered in 2007, Gliese 581c is an exoplanet located about 20 light-years away from Earth in the constellation Libra. It orbits a red dwarf star which is cooler and smaller than our Sun. The intriguing aspect of Gliese 581c is that it is believed to be a rocky planet, similar to Earth, which increases the possibility that it could host life. The presence of a stable atmosphere and suitable temperatures are critical factors in determining the planet's habitability, and scientists have speculated that Gliese 581c may possess these attributes. What makes Gliese 581c even more fascinating is that it challenges our understanding of how life can exist. The conditions on a planet orbiting a red dwarf star differ significantly from those on Earth. Red dwarfs emit less light and heat, leading to unique climates and potential biospheres. As astronomers continue to study similar planets, they are expanding the definition of life's possibilities beyond the familiar conditions of Earth. As we venture further into the cosmos, the significance of Gliese 581c highlights not only our quest to find life beyond our planet, but also our evolving understanding of planetary systems. Each new discovery, including those like Gliese 581c, unveils the vast potential that exists throughout the universe, igniting our curiosity and inspiring future generations of scientists and explorers. Gliese 581c is one of the most intriguing exoplanets discovered to date, located about 20 light-years away from Earth in the constellation Libra. Astronomers first identified this rocky planet in the habitable zone of its star, meaning it orbits within a distance that could allow for liquid water, a crucial ingredient for life as we know it. The interest in Gliese 581c stems from its potential to hold conditions suitable for life, raising exciting possibilities about its surface environment. Observations indicate that Gliese 581c is roughly 1.5 times the size of Earth, suggesting a substantial gravitational pull. However, this raises questions about its atmospheric conditions. Depending on the composition of its atmosphere, which remains largely unknown, Gliese 581c could experience extreme greenhouse warming or maintain a temperate climate. Some models suggest that if the planet has a thick atmosphere rich in gases such as carbon dioxide, it could sustain surface temperatures conducive to liquid water. This notion greenlights the idea of a vibrant environment, possibly including bodies of water or even life. Conversely, scientists have also contemplated a scenario where Gliese 581c might be locked in a tidal state with one side consistently facing its star. This would lead to significant temperature gradients, with scorching conditions on the star-lit side and frigid darkness on the opposite. Such extremes would heavily influence the planet's atmosphere, and by extension, any potential surface conditions, creating an environment where life forms might struggle to adapt. Furthermore, while the existence of a magnetic field could protect Gliese 581c from harmful cosmic radiation, we still know very little about the planet's actual climate. Ongoing research and future observations aim to paint a clearer picture, but Gliese 581c remains a tantalizing possibility in the search for extraterrestrial life, encouraging a great deal of scientific interest and speculation about the conditions that might exist on its surface. Gliese 581c, located about 20 light-years away in the constellation Libra, has captivated astronomers and dreamers alike due to its remarkable resemblance to our own planet. This exoplanet is roughly 1.5 times the size of Earth, placing it in a category known as super-Earths. What truly enhances its allure is its potential to support conditions that could foster life. It occupies a position within its star's habitable zone, where temperatures might allow for liquid water to exist, a fundamental requirement for life as we know it. Yet this similarity also breeds a sense of unease. The environment of Gliese 581c is vastly different from Earth, and it is likely a tidally locked planet. This means one side constantly faces its sun, while the other remains in perpetual darkness. Such extremes could result in inhospitable conditions, with scorching temperatures on one side and frigid climates on the other. The thought of a near-Earth twin, where life may exist yet remain out of reach, prompts questions about what forms life might take in such an alien environment. Moreover, the very existence of planets like Gliese 581c challenges our understanding of what makes a planet habitable. It fuels discussions about the diversity of life beyond our planet, and leads us to ponder the implications of discovering extraterrestrial civilizations that are so similar yet so alien. The prospect that such a world may harbor life forms that are unlike anything on Earth evokes both excitement and trepidation, tapping into deep-seated fears and wonders about the unknown. As we continue to explore these distant worlds, the comparison becomes a mirror reflecting not just our hopes for discovering life out there, but also the fragility of our own planet. The allure and fear intertwined in the study of Gliese 581c remind us of humanity's quest for connection to the cosmos and the mysteries that await us in the great expanse of space. HD 189733b is a fascinating exoplanet located about 60 light-years away from Earth, orbiting a star in the constellation Vulpecula. Its striking blue hue captures the imagination and prompts a closer inspection. However, this vibrant color can be quite misleading. While at first glance one might associate blue with serene waters or clear skies, the reality on HD 189733b is far more perilous. The blue color of this planet is primarily the result of its turbulent atmosphere, which is laden with silicate particles. These tiny glass-like shards form due to extreme conditions within the atmosphere, giving HD 189733b that alluring blue tint. But don't be fooled. The conditions on this planet are chaotic and violent. With wind speeds that can reach up to 1,000 miles per hour, the atmosphere is anything but tranquil. These ferocious winds cause frequent storms that could potentially lead to lethal weather phenomena. In addition to the astonishing winds, HD 189733b experiences a temperature that hovers around 2,000 degrees Fahrenheit. Such extreme temperatures, coupled with the glass-like particles suspended in the atmosphere, create a situation where rain made of molten glass could fall sideways, striking anything in its path with incredible force. This manifests a stark contrast to the inviting look of the planet and emphasizes just how inhospitable this world truly is. By examining HD 189733b, we gain insights into the complex interplay between a planet's appearance and its environmental conditions. The dangers lurking beneath its deceptive beauty underscore the need for careful exploration and observation. This exoplanet serves as a reminder that the universe is full of wonders, but it also harbors hidden perils, waiting for curious minds to uncover their truths. HD 189733b is a remarkable exoplanet located about 60 light-years away from Earth in the constellation of Vulpecula. It has captivated scientists and astronomers alike due to its extreme and hostile weather conditions. This gas giant is classified as a hot Jupiter, a type of exoplanet that is gas-rich and orbits very close to its parent star. The result is an environment with temperatures soaring above 1,000 degrees Celsius, creating a scenario that is nothing short of otherworldly. One of the most astonishing features of HD 189733b is its weather system, characterized by violent storms and winds reaching speeds of over 5,000 kilometers per hour. These intense winds carry particles of glass, which, due to the extreme heat, vaporize into the atmosphere, only to condense and fall back to the surface like deadly shards of glass rain. Imagine a sky filled with glass-like molecules, relentlessly tearing through the dense atmosphere. This lethal precipitation acts like shrapnel, making the conditions on this exoplanet not only inhospitable, but terrifying. The planet's atmospheric composition also contributes to its menacing nature. Comprised primarily of hydrogen and helium, HD 189733b contains clouds rich in silicate particles. When these clouds form, the temperature is so high that the silicate can condense into tiny glass droplets. Consequently, the very rain that falls on HD 189733b is a product of its extreme conditions, creating a hazardous environment that challenges our understanding of planetary atmospheres. These extraordinary weather patterns redefine our perceptions of what a planet can be, pushing the boundaries of the known universe. As we observe HD 189733b and unravel its mysteries, we gain insights into not only whether life can exist in such extreme conditions, but also the complex dynamics of atmospheres outside our solar system. The study of such worlds enriches our understanding of planetary formation and climate systems across the cosmos, reminding us just how diverse and bizarre the universe can be. Simulating the environmental conditions on exoplanets like HD 189733b presents significant challenges for scientists. This exoplanet, located about 63 light-years away, is known for its extreme weather. It has intense winds, blistering heat, and clouds made of glass flecks. The planet's atmosphere is vastly different from what we experience on Earth, and recreating these conditions in a laboratory setting requires innovative approaches and technology. One primary hurdle is the extreme temperatures that HD 189733b endures. The planet orbits its star much closer than Mercury does to our Sun, resulting in surface temperatures that can soar to over 1,000 degrees Fahrenheit. Achieving such temperatures in a controlled environment is one thing, but maintaining them while simultaneously simulating other atmospheric pressures and wind speeds is another significant challenge. Scientists must develop specialized equipment capable of withstanding these harsh conditions while collecting data about the atmospheric phenomena at play. Furthermore, the unique chemical makeup of the planet's atmosphere adds layers of complexity to simulations. Observations suggest that HD 189733b is rich in various gases, including carbon monoxide and water vapor, which react under extreme heat and pressure. Creating an accurate representation of these chemical processes in a laboratory means scientists have to balance not only temperature and pressure, but also the concentration of these different gases. Each variable must be controlled meticulously to draw reliable conclusions about what occurs in such an alien environment. Lastly, there's the challenge of limited observational data. While telescopes have gleaned valuable information about HD 189733b's atmosphere, they cannot capture everything. The more scientists learn, the better their simulations can become, but gaps in our knowledge still exist. This makes it essential for scientists to continually refine their models, leveraging both observations and computational techniques to bridge the gaps in understanding this fascinating world. Each simulation is a step closer to unraveling the mysteries surrounding not just HD 189733b, but the nature of extreme exoplanetary environments as a whole. When we look at HD 189733b, we encounter a world that challenges our understanding of extreme weather. This exoplanet, located about 63 light-years away from Earth, is notorious for its ferocious winds, which can reach astonishing speeds. Research indicates these winds may be traveling at an incredible pace of up to 2,000 miles per hour, far exceeding the strongest hurricanes that we experience here on Earth, which usually max out around 150 miles per hour. The atmosphere of HD 189733b is composed primarily of thick clouds and lethal temperatures that hover around 1,000 degrees Fahrenheit. Such conditions contribute to the violent nature of its weather. The planet also experiences a perpetual state of day and night due to its close orbit to its host star, leading to extreme thermal gradients. This stark difference in temperature between the sunlit side and the dark side creates powerful storms as the heated air rushes to balance this difference, giving birth to those blistering winds. In terms of danger, the winds on HD 189733b present an entirely different league compared to earthly weather systems. The combination of high speeds and hostile atmospheric conditions means that any solid objects in its atmosphere could be whisked away more like projectiles. This is not simply a case of strong winds disrupting structures. Rather, it's a scenario where the very environment is hostile to any form of life as we know it. Moreover, these winds are not just fast, they are also laden with glass-sized particles of molten material, which adds another layer of physical danger. This detail illustrates how unique and extreme this alien world is compared to our own, where, despite the occasional fierce storm, we enjoy a comparatively stable atmosphere. As scientists continue to study exoplanets like HD 189733b, we deepen our appreciation for the rich variety of experiences the universe has to offer. The exoplanet HD 189733b captivates astronomers and enthusiasts alike, not only because of its deep blue appearance, but also due to its violent weather conditions. Located roughly 63 light-years away in the constellation Vulpes, this gas giant has rapidly rotating winds that can reach speeds of over 2,000 miles per hour. These extreme weather patterns alternate between scorching heat and chilling temperatures, creating a complex climate that shapes its stunning visibility. At the heart of HD 189733b's strikingly blue hue are silicate particles found in its atmosphere. When starlight filters through these particles, they scatter blue light more effectively than other colors, leading to that distinctive appearance. The intense winds on HD 189733b carry these silicate particles throughout the atmosphere, mixing with other gases and creating chaotic clouds. When the planet experiences violent storms, these particulates can act like tiny glass shards, resulting in what could be described as a rain of glass blown sideways in the raging winds. This unforgiving and harsh environment provides insight into the extreme conditions that can exist beyond our solar system. Understanding the role of silicate particles not only informs us about the vivid aesthetics of HD 189733b, but also opens a window into exoplanetary atmospheric dynamics. As researchers study this fascinating world, they uncover the complexities of planetary formation and the nuances of different climates in our ever-expanding knowledge of the universe. HD 189733b serves as a reminder that beauty and terror can coexist in the cosmos, reflecting the multifaceted nature of planetary science. The study of our planet's climate holds vital clues for understanding the atmospheres of exoplanets, particularly those that may have hostile conditions. Earth's diverse climate system is shaped by multiple factors, including the composition of the atmosphere, the presence of water, and the influence of the sun. By examining how these elements interact, scientists can make educated inferences about exoplanets orbiting distant stars that exhibit extreme environments. For instance, we can look at Earth's climate history, where periods of extreme heat or ice have had far-reaching impacts on life and geology. By comparing these historical patterns to data from exoplanets with characteristics similar to Earth, we gain insights into what makes a planet potentially habitable or hostile. If a distant planet experiences higher levels of carbon dioxide, like during Earth's past greenhouse periods, it may indicate a runaway effect that could render it too hot for life as we know it. Additionally, studying planets in our solar system with inhospitable conditions, such as Venus and Mars, provides further context. Venus, with its thick, toxic atmosphere and extreme greenhouse conditions, serves as a cautionary tale of what might happen if a planet does not maintain a balance in its climate. On the other hand, Mars, which once had flowing water and a thicker atmosphere, showcases how climate can evolve over time, potentially leading to its current desolate state. By using Earth as a reference point, scientists delve deeper into the climate dynamics of exoplanets, identifying potential indicators of hostility or habitability. Technologies like atmospheric spectroscopy allow researchers to detect gases in exoplanet atmospheres, revealing clues about temperature, pressure, and even potential biological activity. This knowledge not only broadens our understanding of the universe, but also enhances our appreciation for the delicate balance that sustains life on our home planet. Deducing the weather patterns on our planet has been a complex journey, revolutionized by an array of instruments and methods. For centuries, humans relied on simple tools like thermometers, barometers, and wind vanes to measure temperature, atmospheric pressure, and wind direction. These basic instruments laid the groundwork for our understanding of local weather. With advancements in technology, meteorology has transformed into a sophisticated science. One of the most significant breakthroughs in weather observation came with the invention of satellites. Orbiting high above Earth, these satellites provide a comprehensive view of the planet's atmosphere. They capture images and data about cloud cover, temperature variations, and storm systems. This satellite imagery is crucial for both short-term weather forecasts and long-term climate studies, enabling meteorologists to visualize weather patterns across vast distances, which was previously unfeasible. Additionally, ground-based radar systems play a vital role in detecting precipitation and monitoring severe weather events like hurricanes and tornadoes. Doppler radar, for instance, allows scientists to observe the movement and intensity of storms, providing detailed information on how these systems develop and interact. This immediacy in tracking weather phenomena has empowered forecasters to issue timely alerts and warnings, enhancing public safety. Finally, numerical weather prediction models have emerged as a cornerstone of modern meteorology. Employing complex algorithms and vast amounts of atmospheric data from various sources, these models simulate the atmosphere's behavior. By analyzing interactions within the atmosphere, scientists can predict weather patterns with increasing accuracy. The combination of traditional instruments, satellite technology, radar systems, and advanced computational models illustrates a remarkable evolution in our understanding of the Earth's weather systems, shaping the way we respond to the elements every day. HD 189733b is a fascinating exoplanet located about 63 light-years away, and it stands as a remarkable example of how diverse the universe can be in terms of planetary conditions. This gas giant orbits its star closely, completing a revolution in just a little over 2 days. The combination of its proximity to a bright star and its dense atmosphere creates extreme environments that defy our typical expectations for habitable conditions. The weather on HD 189733b is nothing short of astonishing. Winds here can reach speeds of up to 2,000 miles per hour, making them some of the fastest in the cosmos. Moreover, the planet experiences conditions of intense heat and violent rain, not of water, but of molten glass, which is driven sideways by those brutal winds. Such an environment forces us to reconsider our notions about where life might exist and what forms it could potentially take, especially in extreme situations. Historically, the concept of habitability has been largely tied to environments similar to Earth, where temperatures allow for liquid water and a stable atmosphere. However, HD 189733b pushes the boundaries of these ideas by demonstrating that life could theoretically survive in conditions we currently deem inhospitable. This prompts important questions about the resilience of life and the conditions under which it might thrive. It challenges our understanding by suggesting that life might adapt to extreme environments far removed from what we consider suitable. As we continue to explore exoplanets like HD 189733b, we find that our definitions of life and habitability are not as rigid as once thought. These extreme worlds force scientists to expand their imaginations about the possible forms and adaptations that life might take. Ultimately, each discovery about these distant planets teaches us that the universe is rich with possibilities, urging us to keep questioning, exploring, and understanding the myriad ways life could adapt and endure. HD 189733b is a remarkable exoplanet that captivates both scientists and storytellers due to its astonishing characteristics and the mystery that surrounds it. Located about 63 light-years away in the constellation Vulpecula, this planet challenges our understanding of what a world can be. Its most striking feature is its vibrant blue color, which is a striking contrast to the fiery storms that rage across its atmosphere. This vivid hue is caused by silicate clouds, which scatter light in a way that creates a dazzling appearance. Another fascinating aspect of HD 189733b is its extreme weather conditions. The planet is classified as a hot Jupiter, which means it is a gas giant orbiting very close to its host star. Temperatures can soar above 1,000 degrees Celsius, resulting in winds that whip through its atmosphere at speeds exceeding 2,000 kilometers per hour. These intense storms and harsh environments evoke images reminiscent of science fiction narratives, making it a perfect subject for storytellers exploring the possibilities of alien worlds. Furthermore, HD 189733b orbits its star in just over 2 days, leading to a perpetual face-off between day and night on opposite sides of the planet. Such unique orbital characteristics spark the imagination, allowing scientists and laypeople alike to speculate about the atmospheric dynamics and potential weather systems in such a tantalizingly different world. As we unravel the complexities of planets like HD 189733b, we come to appreciate not just what is possible in our universe, but the potential for life, environments, and experiences beyond our own. This exoplanet serves as a symbol of the limitless possibilities that await us in the cosmic landscape, making it a beacon of fascination and inquiry for researchers and dreamers. Astronomers employ advanced techniques to capture the stunning colors of exoplanets, such as HD 189733b, which is located about 65 light-years from Earth. The primary method used is known as transit photometry. This technique involves monitoring the light from a star and observing the slight dimming that occurs when a planet passes in front of it. The light that filters through the planet's atmosphere during this transit carries crucial information about its composition and temperature. By analyzing the light spectrum that is absorbed or scattered by the atmosphere of the exoplanet, astronomers can discern its chemical makeup. HD 189733b is particularly fascinating because it displays a striking blue hue, which is attributed to the scattering of light by the planet's atmosphere, similar to how Earth's sky appears blue. This blue color suggests that the atmosphere contains a significant amount of silicate particles and possibly clouds, hinting at a tumultuous weather system imprinted with high-speed winds and dramatic atmospheric phenomena. The vivid colors captured by astronomers reveal more than just aesthetic beauty. They provide insights into the conditions on these distant worlds. The presence of specific gases such as water vapor and methane can also be inferred from these color patterns, giving us clues about the planet's potential to support life or its extreme environmental conditions. Each color observed leads to a deeper understanding of how these planets form and evolve over time, enriching our knowledge of the cosmos. Such incredible discoveries are only possible thanks to powerful telescopes equipped with state-of-the-art imaging technologies. These tools allow scientists to observe exoplanets with remarkable precision, revealing details that were once unimaginable. As we look at the colors of HD 189733b and other exoplanets, we unravel the complex tales they tell about the universe, painting a vivid picture of worlds far beyond our own. Kepler 10b, discovered in the early days of exoplanet research by NASA's Kepler mission, stands out as one of the hottest exoplanets known to science. What sets it apart is its proximity to its host star, a sun-like star located around 520 light-years away in the constellation Draco. This close orbit means that Kepler 10b completes a full revolution around its star in just over 20 hours, leading to extreme temperature conditions that make it a fascinating subject of study. The temperatures on Kepler 10b soar to scorching levels, easily exceeding 1,500 degrees Celsius. Such relentless heat is primarily due to the intense stellar radiation it receives, a direct consequence of its tight orbit. As one of the first rocky exoplanets confirmed, Kepler 10b challenges our understanding of planetary formation and evolution. That said, it's not a hospitable environment. Any surface conditions are likely inhospitable to life as we know it. Moreover, Kepler 10b serves as a vivid example of the diversity of planetary systems beyond our own. While Earth-like planets have garnered significant interest, the existence of such extreme worlds highlights the variety of environments that can exist in the cosmos. In contrast to our blue planet, Kepler 10b showcases the extremes of temperature and composition, illustrating that not all exoplanets can support conditions suitable for life. Discoveries related to Kepler 10b provide valuable insights into the dynamics and characteristics of hot, rocky exoplanets. As astronomers continue to explore worlds beyond our solar system, Kepler 10b presents an essential piece of the cosmic puzzle, enhancing our understanding of the universe and the myriad possibilities it holds. Kepler 10b orbits very close to its star, a process known as proximity. This means that it is subjected to intense solar radiation, much stronger than what we experience here on Earth. To put it into perspective, Kepler 10b is so close to its star that a full orbit takes only about 20 hours. As a result, one side of the planet is constantly bathed in heat and light, while the other remains in perpetual darkness. The immense gravitational pull from its star causes Kepler 10b to experience extreme surface temperatures, with estimates suggesting that the side facing the star can reach scorching temperatures in excess of 1,000 degrees Celsius. This is far beyond the threshold for liquid water, casting the notion of a habitable environment as highly unlikely. The side that faces away from the star would be considerably cooler, but temperatures would still be far colder than what most life forms on Earth could endure. Additionally, the planet's rocky surface would likely be marked by violent volcanic activity, fueled by the intense heat. This heat may also lead to the presence of molten rock, creating a surface dominated by vast lava plains and possibly even clouds of vaporized rock and gas. The rapid temperature differential between the day and night sides could contribute to severe atmospheric phenomena, if any atmosphere exists at all given the characteristics of this harsh environment. Thus, Kepler 10b represents one of those intriguing examples in our exploration of exoplanets. While it might not host life as we know it, its extreme conditions allow scientists to gain valuable insights into planetary formation and the variety of environments that exist in the universe. Through studying planets like Kepler 10b, we can better understand how proximity to a star can shape not just the temperature, but also the very nature of a planet itself. Exploring a planet devoid of atmosphere like Kepler 10b opens a fascinating window into the dynamics of celestial bodies and their environments. Kepler 10b, located over 500 light-years from Earth, is known for its extreme conditions. It orbits very close to its star, completing a rotation in just 20 hours. Without an atmosphere, this planet experiences harsh temperature fluctuations, with scorching daytime heat and frigid nighttime cold. Such extremes challenge our understanding of how planets can maintain a stable environment. The absence of an atmosphere profoundly affects the planet's surface conditions. For instance, without atmospheric pressure, a planet cannot support liquid water, a crucial component for life as we know it. Instead, water on Kepler 10b would exist solely as ice or vapor, depending on the temperature at any given moment. This property raises significant questions about the fundamental requirements for habitability on other planets, enhancing our understanding of where life could potentially thrive. Moreover, studying planets like Kepler 10b enriches our knowledge of planetary formation and evolution. Most planets have some form of atmosphere that influences their geology and climate. By contrasting these atmospheric worlds with those that lack atmospheres, scientists can refine their models of planetary development and the myriad factors that contribute to a planet's surface characteristics. Additionally, Kepler 10b serves as an experimental ground for theories relating to heat retention and energy balance. With its rigid surface and lack of insulation from an atmosphere, it provides clear data on how radiative heat from stars behaves. This information can help astrophysicists understand not only exoplanets like Kepler 10b, but also our own planet's past and the fate it may face in the distant future. Such insights might reshape our comprehension of planets beyond our solar system and increase the intrigue surrounding the diverse environments that exist throughout the cosmos. Kepler 10b emerged as one of the very first rocky exoplanets discovered due to its remarkable journey in our quest to understand celestial bodies beyond our solar system. The breakthrough occurred with the launch of NASA's Kepler Space Telescope in 2009, which aimed to find Earth-like planets in the habitable zones of stars. Kepler's unique ability to continuously monitor stars allowed it to detect the subtle dimming caused when a planet transits or passes in front of its host star. In January of 2011, after analyzing data collected by the Kepler telescope, astronomers confirmed Kepler 10b as a planet orbiting a star approximately 20,000 light-years away in the constellation Cygnus. What made Kepler 10b particularly fascinating was its size and density, which suggested it was rocky, unlike many other exoplanets that had been discovered up to that point, which tended to be much larger gas giants. The determination of Kepler 10b's rocky nature came from its size, being about 1.5 times the size of Earth, and its mass, which was found to be about 4.5 times greater. These measurements indicated that its composition was likely similar to terrestrial planets in our own solar system. Its proximity to its star, a blazing hot sun, led to scorching surface temperatures, which made the conditions quite severe. This remarkable planet took only about 20 hours to complete one orbit around its star, a strikingly fast pace that contributed to its classification amid a new generation of exoplanets. The discovery of Kepler 10b was pivotal not only for adding a rocky planet to the roster of known exoplanets, but also for igniting further interest in cosmic research. It demonstrated that rocky exoplanets were not only a possibility, but that many could exist in various star systems throughout the universe. Each insight gleaned from such discoveries propels the scientific community toward understanding the diversity of planets, their formation, and their potential for supporting life outside Earth. Kepler 10b is a fascinating astronomical discovery that has expanded our understanding of how planets form and evolve, especially those that orbit close to their stars. Discovered by NASA's Kepler mission, this exoplanet is located about 25 light-years away from Earth in the constellation Cygnus. What makes Kepler 10b particularly intriguing is its classification as a rocky planet, very similar to Earth, but with a critical difference. It orbits its star at a remarkably close distance. This proximity to its star results in extreme temperatures, reaching over 1,000 degrees Celsius. Such intense heat has profound implications for the planet's formation and evolution. First, it suggests that Kepler 10b likely formed further out in the protoplanetary disk, where conditions were cooler and later migrated inward. This kind of movement is increasingly recognized as a common process in planetary systems, where dynamic interactions can push planets into tighter orbits around their stars. Moreover, Kepler 10b's surface is thought to be rather inhospitable, possibly featuring a molten landscape due to the immense heat it endures. This brings up interesting questions about the durability of planetary compositions under such extreme conditions. While some rocky planets might weather the harsh environment, others, like Kepler 10b, may lose significant amounts of their atmosphere, if they ever had one to begin with. Thus, it provides a real-world example of how close proximity to a star can alter a planet's physical and chemical characteristics dramatically. The insights from Kepler 10b challenge our previous notions of where planets can exist and how they develop. It highlights the complexity of planet formation processes, showing that the conditions we once thought were necessary for rocky planets like Earth might not be universally applicable. As we continue to explore exoplanets, Kepler 10b serves as a key piece of the cosmic puzzle, inviting us to rethink the potential for life and habitability across the universe. Kepler 10b, a rocky exoplanet located over 500 light-years away, is known for its anomalously high surface temperatures, likely exceeding 1,000 degrees Celsius. This extreme heat poses significant challenges for scientists attempting to understand its composition and the conditions present on its surface. To address this, researchers have creatively turned to laboratory simulations, employing techniques that replicate the intense thermal environments of such alien worlds. One popular method involves using specialized ovens known as high-temperature furnaces. In these controlled environments, scientists can heat samples of material thought to be similar to Kepler 10b's rocky surface. Through this process, they examine how these materials behave under extreme temperatures and pressures, allowing them to glean insights into the planet's geological processes and potential atmospheric components. Another innovative approach relies on laser-induced heating techniques. By focusing powerful lasers onto small samples, researchers can create localized high temperatures that mimic the conditions on Kepler 10b. This method allows for real-time observation of the physical and chemical changes that occur when materials are subjected to these intense heat levels. Such experiments reveal crucial information about the stability of compounds and minerals that may exist on the planet, enhancing our understanding of its geological history. Through these laboratory simulations, scientists have not only expanded their knowledge about Kepler 10b, but have also gained insights that may apply to other extreme environments beyond our solar system. By unraveling the mysteries of such distant planets, we deepen our appreciation for the diverse occurrences in the universe and how our own planet fits into this grand cosmic tapestry. When we turn our gaze to Venus, the second planet from the Sun, we encounter an environment unlike any other in our solar system. Often referred to as Earth's twin, Venus stands out due to its extreme atmospheric conditions and scorching surface temperatures that can reach up to around 800 degrees Fahrenheit. The surface is characterized by vast plains, towering volcanoes, and even what appear to be ancient riverbeds, hinting at a complex geological history. Despite the harsh conditions, several intriguing remnants of surface materials can be found. The landscape is primarily composed of basalt rock formed from the solidification of lava. This volcanic activity suggests that Venus has experienced significant geological transformation over millennia. Astronomers believe that materials such as sulfur and iron are abundant, giving the planet its distinctive yellowish hue when viewed through a telescope. The presence of these elements indicates a strong volcanic activity that may still occur beneath the surface. Another fascinating aspect of Venus's surface material is the existence of certain forms of mineral deposits, particularly in the highland areas. These minerals, primarily composed of volcanic rock, include things like granite and other silica-rich compositions. The discovery of such materials suggests that Venus once had a much more Earth-like environment, potentially with water on its surface. Although water is now scarce, the remnants of its geological past reveal that conditions may have once been significantly more hospitable. As researchers continue to study Venus through advanced spacecraft missions, the prospect of uncovering more about these surface materials remains exciting. Each discovery not only helps us understand Venus's unique climate and geological history, but also offers clues about planetary evolution. These remnants tell a story of transformation that, while hidden under a thick, toxic atmosphere, still captures our imagination and fuels our quest for knowledge about our neighboring worlds. The discovery of Kepler 10b has sparked fascinating discussions among scientists about the boundaries of where life could potentially exist in our universe. This exoplanet, located about 25 light-years away from Earth, orbits its star, Kepler 10, at a blistering pace. It completes one orbit in just about 20 hours. One of the most striking features of Kepler 10b is its composition. Despite being rocky, it is exposed to extreme temperatures that are far from conducive to life as we know it. Traditionally, scientists defined habitability zones, often called Goldilocks zones, as regions around stars where conditions are just right for liquid water to exist. These zones take into account various factors such as the distance from a star and the type of star it is. However, the extreme conditions on Kepler 10b challenge these established ideas. Scientists have observed that this planet is much too close to its host star, leading to surface temperatures that likely reach well over 1,000 degrees Celsius. What makes Kepler 10b even more intriguing is the possibility that it may not be an isolated anomaly. Its existence prompts researchers to reconsider the robustness of their models about planetary formation and habitability. They now contemplate a broader range of environments that could harbor life, perhaps in ways that we have yet to fully understand. This discovery suggests that the potential for life could lie in unexpected places, and that we might need to expand our criteria beyond mere proximity to the star. Kepler 10b serves as a catalyst for a deeper understanding of the cosmos. It encourages scientists to explore the diverse conditions that might support life, or at least resemble the complex characteristics of Earth. As we continue to search for planets beyond our solar system, discoveries like Kepler 10b remind us just how much we still have to learn about the universe and our place in it. Detecting distant and potentially hostile planets, particularly those situated many light-years away from Earth, hinges on a combination of advanced technology and innovative methodologies. The first major breakthrough came with the development of highly sensitive telescopes, particularly space-based observatories. Instruments such as the Hubble Space Telescope, and more recently, the Transiting Exoplanet Survey Satellite, have enabled astronomers to observe celestial bodies beyond our solar system with unprecedented clarity. One of the most significant techniques used to find these distant worlds is the transit method. This method involves observing a star and looking for slight dips in brightness that occur when a planet passes in front of it. Improvements in photometry, the science of measuring light, have allowed scientists to detect these minute changes with remarkable precision, even when the planets are light-years away. Another major technological advancement is direct imaging, which allows astronomers to capture pictures of exoplanets. This technique requires sophisticated coronagraphs and adaptive optics to block out the bright light of stars, revealing planets situated much closer to them. Recent innovations in these areas have made it possible to not only find planets, but also to analyze their atmospheres, looking for signatures that might indicate habitability or hostility. In addition to these observational techniques, advancements in data processing and analysis are crucial. The vast amounts of data gathered by modern telescopes entail complex algorithms and machine learning models to sift through signals and identify potential planetary candidates. Together, these technological strides have transformed our ability to explore distant planets, revealing a universe that can be both familiar and frighteningly alien. Kepler 10b is a fascinating celestial body that has captured the attention of astronomers since its discovery. With a size comparable to that of Earth, yet significantly more massive, Kepler 10b weighs in at nearly 5 times our planet's mass. This substantial increase in weight leads to a much higher density. In fact, its density is more akin to that of rocky planets, which suggests a composition rich in heavier materials. The immense gravitational force exerted by this dense planet has profound implications for its surface. Given its proximity to its star, Kepler 10b orbits at such a close range that it receives extraordinarily high levels of stellar radiation. This intense heat is sufficient to keep its surface in a molten state, creating conditions reminiscent of a lava world. Imagine a planet where the ground is constantly flowing with lava, and temperatures soar far beyond what we experience on Earth. Moreover, the combination of Kepler 10b's dense makeup and its volcanic surface reveals much about exoplanetary environments. Scientists believe that the extreme heat coupled with its heavy elements contributes to a dynamic, potentially active surface. Volcanic activity isn't merely a possibility, it's likely a defining feature of the planet as it struggles against the unrelenting temperature extremes. Studying Kepler 10b helps scientists understand not just the characteristics of similar exoplanets, but also the processes that govern planetary formation and evolution in our universe. The extraordinary conditions that make Kepler 10b a lava world serve as a reminder of the incredible diversity found beyond our own solar system, expanding our knowledge and igniting excitement about the cosmos. WASP 121b is a fascinating exoplanet that has captured the attention of astronomers because of its extraordinary meteorological phenomena. This planet, located approximately 850 light-years away from Earth, is classified as a gas giant, and what sets it apart is its extreme temperature and atmospheric conditions. Temperatures on WASP 121b can reach a sweltering 1,600 degrees Celsius, hotter than most molten lava flows on our own planet. One of the most terrifying aspects of WASP 121b's atmosphere is its incredible winds. These winds can whip around the planet at about 7,000 kilometers per hour. To put that into perspective, that is roughly 7 times the speed of sound on Earth. Such ferocious winds create violent storms that contribute to a chaotic environment. Additionally, WASP 121b experiences rains made not of water but rather molten glass. Yes, you heard that right. Glass. Imagine tiny blades slicing through the air, adding to the peril of this already inhospitable world. Moreover, this exoplanet orbits very close to its host star, causing its day side to be unbearably hot, while the night side is significantly cooler. This stark temperature gradient contributes to the extreme weather patterns observed. The heat on the day side drives intense atmospheric circulation, potentially leading to dramatic shifts in weather as air moves from the scorching daytime heat to the cooler nighttime conditions. These phenomena not only challenge our understanding of planets, but also paint a vivid picture of how diverse planetary atmospheres can be. It serves as a reminder of the extremes that exist beyond our own solar system, where conditions can be both beautifully strange and frighteningly harsh. Exploring WASP 121b and similar exoplanets enhances our comprehension of planetary science and the diversity of worlds in the universe. WASP 121b is an extraordinary exoplanet located about 800 light-years away from Earth, and it's unlike any planet in our solar system. This gas giant is classified as a hot Jupiter. It orbits extremely close to its parent star, resulting in surface temperatures soaring to over 2,500 degrees Celsius. Such scorching heat plays a pivotal role in the formation of exotic metal clouds in the planet's atmosphere. The intense conditions on WASP 121b lead to the vaporization of various metals, including sodium, potassium, and iron. At these extreme temperatures, these elements exist in gaseous form. As the planet rotates and interacts with the incredible heat from its star, the processes of condensing and cooling become significant. As the hotter gases rise, they eventually cool down, allowing them to condense into clouds of metals. These metallic elements don't just linger, they create shimmering reflective clouds that can be observed with powerful telescopes. What's fascinating is that the combination of these metal clouds not only affects the atmospheric composition, but also alters the weather patterns on WASP-121b. The presence of metals can lead to unique phenomena where the clouds can produce various kinds of precipitation, albeit not in the way we experience water rain on Earth. Instead, it might mean droplets of molten metal falling through the scorching atmosphere, a concept that sounds almost surreal but is supported by the unique conditions observed on this alien planet. Thus, WASP-121b serves as a stunning illustration of the diversity of planetary systems beyond our own. The existence of metal clouds challenges our understanding of planetary atmospheres and highlights the incredible variety of conditions that can exist in the universe. Observing such phenomena expands our knowledge and sparks curiosity about what more awaits us in the cosmos. WASP-121b is a fascinating exoplanet located about 800 light-years away from Earth, orbiting a distant star in a tight, scorching embrace. This planet is classified as a hot Jupiter, which means it is a gas giant similar to Jupiter but orbits its star at an incredibly close distance. Due to this proximity, WASP-121b experiences extreme temperatures that can soar above 2000 degrees Celsius. Such blistering heat plays a key role in shaping its unique atmospheric conditions. At these intense temperatures, the atmospheric composition of WASP-121b undergoes some intriguing transformations. Hydrogen and helium, which dominate the atmospheres of many gas giants, become incredibly volatile under this heat. In fact, the environment is so extreme that heavy metals like iron and magnesium vaporize, remaining suspended in the atmosphere. This unusual phenomenon leads to the presence of what scientists call metal clouds, creating a striking contrast to the familiar cloud formations found on planets like Earth. Moreover, the extreme heat leads to significant temperature gradients between the day side and the night side of the planet. The side that faces the star becomes searingly hot, while the opposite side exists in perpetual darkness, creating a sharp division in atmospheric behavior. This results in powerful winds that transport heat from the day side to the night side, driving dynamic weather patterns that are both unpredictable and extreme. Such conditions could lead to fierce storms, unique cloud formations, and perhaps even rain made of molten glass. Ultimately, the extreme heat of WASP-121b gives rise to an array of bizarre atmospheric conditions, showcasing the diverse possibilities that exist in the universe. The interactions between temperature, composition, and dynamics create an environment that challenges our understanding of planetary atmospheres, giving us a glimpse into the fascinating complexities of worlds beyond our own. Each study of such planets adds to the grand tapestry of cosmology, propelling us to ask even more questions about the diversity of planetary systems. WASP-121b is a fascinating exoplanet located about 800 light-years from Earth. This planet intrigues scientists due to its unique atmosphere, which is unlike anything found in our solar system. The study of WASP-121b's atmosphere has employed a variety of scientific methods, primarily focusing on spectroscopy and transit observations. Spectroscopy is a powerful technique that allows scientists to analyze the light that passes through an exoplanet's atmosphere during a transit. When WASP-121b passes in front of its host star, some of the star's light filters through the planet's atmosphere. By measuring the light spectrum, researchers can identify specific chemicals present in the atmosphere based on how the light is absorbed at different wavelengths. This has revealed the presence of vital elements and compounds that shape our understanding of this alien world. Observations from powerful space telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, have been crucial in examining WASP-121b's atmospheric characteristics. These observations allow scientists to track changes in brightness as the planet transits, further refining their analysis of the materials within its atmosphere. The ability to observe such distant objects with sophisticated technology has opened up new avenues for researching not just exoplanets, but also their potential for hosting life. In addition, computer modeling and simulations play a significant role in understanding the complexities of WASP-121b's atmosphere. By comparing observed data with theoretical predictions, scientists can glean insights into climate patterns and weather phenomena that might occur there. The study of WASP-121b is a remarkable intersection of observation, theory, and technological advancement, expanding the boundaries of what we know about the universe and its diverse array of planetary systems. The study of metal cloud formations unveils a fascinating aspect of atmospheric science that challenges our traditional understanding of weather patterns, especially in extreme environments. Typically, when we think of clouds, we envision water vapor condensing into tiny droplets, forming fluffy cumulus shapes in our sky. However, in specific locales, such as those found in extreme conditions, like Uranus or Neptune, scientists have discovered clouds that contain metals. These clouds can form from various processes, including intense atmospheric pressure and unique temperature variations. Interestingly, the presence of metals in these clouds could influence weather systems in ways we are still unraveling. For instance, clouds composed of metal droplets can affect radiation absorption and heat distribution in the atmosphere. This may lead to different thermal dynamics compared to clouds formed solely from water vapor. These dynamics can alter storm patterns, precipitation, and even surface temperatures in extreme environments, providing insights not only into planetary atmospheres, but also into Earth's own weather phenomena under extreme conditions. The research opens up new avenues for understanding how wind patterns and thermal convection respond when metals are present in the atmosphere. This is particularly relevant in the study of exoplanets, where scientists attempt to predict weather systems in environments vastly different from our own. By comparing these metal clouds with similar cloud formations in Earth's atmosphere, researchers can also refine their models of weather prediction under severe conditions, enhancing our ability to forecast climate anomalies. As we deepen our understanding of these metal cloud formations, we uncover the intricate relationships between atmospheric composition and weather behaviors in the universe. The potential for discovering new weather systems on distant worlds adds an exciting dimension to our quest for knowledge about the cosmos and our place within it. The discovery of ultraviolet-induced destruction of water molecules in the atmosphere of WASP 121b is significant for several reasons. First and foremost, it provides crucial insights into the complex atmospheric chemistry of exoplanets, especially those that orbit very close to their stars. WASP 121b is a gas giant located approximately 850 light-years away from Earth. It has a scorching atmosphere with temperatures that can reach over 2,000 degrees Celsius. In such extreme environments, water may not behave as we expect based on Earth's conditions, leading to unexpected chemical interactions. Ultraviolet radiation from its nearby star plays a pivotal role in this atmospheric chemistry. The high-energy ultraviolet light can break apart water molecules into their constituent elements, hydrogen and oxygen. This process, known as photodissociation, reveals how these massive planets manage their atmospheric composition and what happens to essential molecules when subjected to intense stellar radiation. The dynamics of these reactions can change our understanding of how water vapor behaves on exoplanets and influence the potential habitability of other celestial bodies. Moreover, the destruction of water molecules in WASP 121b's atmosphere highlights the planet's unique atmospheric dynamics. With sufficient energy from its host star, the remnants of hydrogen and oxygen can escape into space, further raising questions about the long-term stability of such extreme atmospheres. Understanding these processes helps astronomers gauge how atmospheres evolve over time on different planets, and may offer clues about the atmospheric characteristics of distant worlds. Finally, this discovery invites broader questions about the formation of planets and the potential for life beyond our solar system. By exploring the interactions between ultraviolet radiation and key molecules like water, we can deepen our understanding of planetary systems. This knowledge can ultimately inform the search for habitable environments elsewhere in the universe, painting a more nuanced picture of how life may emerge under varying cosmic conditions. WASP 121b is a fascinating exoplanet that has captivated scientists and enthusiasts alike due to its extreme atmospheric conditions. This gas giant is located over 800 light-years away from Earth in the constellation Centaurus. What makes WASP 121b particularly intriguing is its extremely close orbit around its host star, which leads to significant temperature variations on its surface. Daytime temperatures can soar to a blistering 1,300 degrees Celsius, while nighttime temperatures can plummet drastically. The planet exhibits what is known as day-night temperature variation, but not in a way that strictly resembles what we might see on Earth. Because WASP 121b is tidally locked, one side always faces its star while the other side remains in perpetual darkness. This tidally locked nature causes the day side to be extremely hot, while the night side has the potential to be much cooler. However, the important aspect here is how atmospheric circulation works to redistribute heat across the planet, providing a balance to these extremes. The atmosphere of WASP 121b is thought to contain a high concentration of metals, including vaporized sodium and potassium. This metallic content contributes to unusual thermal dynamics as these elements absorb and re-emit heat. Winds in WASP 121b's atmosphere play a critical role as well, transporting heat from the day side to the cooler night side. This process functions much like ocean currents on Earth, redistributing warmth and helping to moderate temperature differences. Recent observations have also suggested the presence of large-scale weather systems, which could further facilitate this heat exchange. Scientists believe that conditions on the planet are dynamic and ever-changing, leading to the possibility of clouds that shift heat from one region to another. Thus, despite the extreme temperatures that are characteristic of its surface, WASP 121b demonstrates a remarkable ability to balance these extremes through atmospheric interactions and circulation patterns. This extraordinary mechanism offers valuable insights into how other exoplanets might behave under similar circumstances. WASP 121b is a fascinating exoplanet that orbits its star at an extremely close distance, leading to some extraordinary atmospheric phenomena. This planet provides astronomers with a unique opportunity to study what is known as a hot Jupiter, a type of gas giant that has a temperature hot enough to melt metals. Observations of WASP 121b reveal extreme temperatures that vary drastically from day to night, and this dramatic temperature difference drives powerful winds and weather systems that are unlike anything found in our solar system. One of the key lessons from WASP 121b is the role of atmospheric circulation. As the planet rotates, heat from its star creates immense temperature gradients, which in turn generate strong winds. These winds can carry hot gases from the day side to the night side, resulting in a redistribution of heat. This phenomenon is vital for astronomers when making analogies to other hot Jupiters, as they can use models based on WASP 121b to predict how weather patterns might evolve on similarly extreme planets. Additionally, WASP 121b has shown signs of complex chemistry in its atmosphere, including the presence of metals like iron and titanium. Such findings highlight the interplay between temperature and atmospheric composition, suggesting that high-energy environments lead to unique chemical reactions. By understanding the atmospheric dynamics of WASP 121b, astronomers gain insights into the types of chemical processes that could occur on other hot Jupiters, contributing to the broader understanding of planetary atmospheres. Ultimately, the study of WASP 121b aids astronomers in refining their predictive models of exoplanetary weather. By analyzing the processes at work on this extreme world, scientists can better grasp how different environmental conditions influence atmospheric dynamics. This knowledge is not only pivotal for understanding WASP 121b itself, but also helps unravel the mysteries of a diverse array of distant worlds where similar energetic interactions may occur. WASP 121b is a fascinating exoplanet, located over 800 light-years away in the constellation Puppis. It is classified as a hot Jupiter, a type of gas giant that orbits very close to its star, leading to extreme temperatures. The atmosphere of WASP 121b has been the focus of intense study, particularly because it is characterized by a rich variety of chemical interactions. This unique environment provides a valuable laboratory for astronomers and chemists alike. One of the most striking features of WASP 121b's atmosphere is the presence of complex molecules such as iron and titanium. These elements exist in gaseous form due to the planet's scorching temperatures, which can rise to over 2,000 degrees Fahrenheit. Such extreme conditions allow researchers to study not only the makeup of the atmosphere, but also how these materials interact under high-energy conditions. For instance, the study of clouds and hazes in the atmosphere reveals how various chemicals can affect light absorption and scattering, leading to a greater understanding of atmospheric dynamics. Investigating the chemical interactions within WASP-121b's atmosphere also informs us about the potential for similar exoplanets that may be discovered in the future. By understanding how extreme temperatures and pressures can shape the presence and behavior of various molecules, scientists can refine their models when they discover new planets. For instance, if researchers can determine how specific compounds form or dissolve under these conditions, they can make predictions about the atmospheres of other gas giants, even those located in different solar systems. Ultimately, the insights gained from WASP-121b could pave the way for groundbreaking research into planets that have yet to be observed. As telescope technology advances, astronomers are increasingly able to analyze the atmospheres of distant worlds. The chemical signatures identified in WASP-121b may serve as a comparative tool, allowing scientists to decipher the environmental conditions of new exoplanets. With each revelation, our understanding of the universe's diversity expands, opening doors to new discoveries that could redefine how we view planetary systems far beyond our own. WASP-121b is a truly extraordinary exoplanet, known for its unique characteristics that distinguish it from the many other hot Jupiters discovered beyond our solar system. One of the most remarkable features of this gas giant is its extreme atmospheric conditions. With a temperature soaring to about 2,500 degrees Celsius, WASP-121b is situated so close to its host star that its atmosphere is heated to a point where it can evaporate. This high temperature is significantly hotter than many of its peers, making WASP-121b a real standout. Another fascinating aspect of WASP-121b is its unusual atmospheric composition. Studies have revealed that its atmosphere contains a blend of heavy metals, including iron and magnesium, which exist not as condensed particles, as we might find on cooler planets, but rather in a gaseous state. This phenomenon contributes to what scientists call thermal inversion, where temperatures unexpectedly increase with altitude. This inversion leads to the formation of clouds made up of these metals, creating a strikingly colorful display in its upper atmosphere, one that is entirely unlike anything found in our solar system. Additionally, WASP-121b's orbit offers a captivating glimpse into tidal forces at work. It completes a single orbit around its star in just about 30 hours, which is incredibly quick. This rapid orbit results in extreme tidal lock, meaning that one side of the planet is perpetually facing its sun, while the other side remains shrouded in darkness. This stark contrast creates dramatic temperature differences across the planet, enhancing the already brutal environment found on its surface. WASP-121b shines in the celestial crowd of hot Jupiters due to its eye-popping temperatures, unusual atmospheric composition rich in metals, and its fascinating orbital dynamics. The insights gleaned from studying such a unique world not only deepen our understanding of planetary science, but also pose new questions about the diversity and complexity of planetary systems in the universe. TRES-2b, an exoplanet located about 50 light-years away from Earth, holds the title of the darkest known planet in the universe. Its remarkable darkness is primarily due to its unique atmospheric composition, which absorbs an astonishing 99% of the light that hits it. This extreme light absorption makes it incredibly difficult to observe, as it reflects only a tiny fraction of sunlight. The reason for such low reflectivity lies in the presence of various materials in its atmosphere. TRES-2b is believed to contain substances like vaporized sodium, potassium, and potentially other elements that contribute to its absorbing qualities. The thick clouds in its atmosphere may also play a critical role, as they enhance this absorption by scattering light in ways that prevent it from escaping back to space. Furthermore, TRES-2b orbits very close to its host star, Kepler 13a, resulting in intense heating of its surface. With temperatures soaring above 1,000 degrees Fahrenheit, the planet is unlikely to support traditional forms of reflective surfaces like ice or water. Instead, the extreme heat alongside the unique atmospheric conditions creates an environment where light doesn't escape, rendering TRES-2b a dark, mysterious world. In contrast to many planets we observe, which display vibrant colors and reflectivity due to different surfaces or atmospheric components, TRES 2b stands out as a cosmic enigma. It invites scientists to explore the complexities of light absorption and the fascinating properties of planetary atmospheres. The quest to understand such unique worlds helps us appreciate the diversity of the universe and may shed light on the formation and evolution of planetary systems beyond our own. TRES 2b is an exoplanet that has captured the attention of astronomers due to its strikingly low reflectivity, making it one of the darkest planets known. In fact, its albedo, a measure of reflectivity, is remarkably low, less than 1%. This means that almost all the light that hits its surface is absorbed rather than reflected. In contrast, many other planets, including our own Earth, have higher albedos due to clouds, oceans, and ice that reflect sunlight back into space. The extreme darkness of TRES 2b can be attributed to its atmosphere, which contains very thick layers of gas, likely rich in sodium and potassium. These elements contribute to its black appearance by absorbing most of the light that reaches the planet. In comparison, planets like Saturn and Jupiter, with their colorful cloud bands and bright atmospheres, reflect a significant amount of light due to their composition and weather patterns. Reflectivity plays a crucial role in determining a planet's temperature. Since TRES 2b absorbs so much light, it becomes incredibly hot, with surface temperatures soaring to around 1,000 degrees Celsius. This intense heat translates into a very different environment compared to planets with higher albedos, which may have more temperate climates due to the sunlight they reflect. In examining TRES 2b alongside other celestial bodies, we gain insights into the diverse range of planetary environments that exist beyond our solar system. Understanding the factors that influence reflectivity not only illuminates our knowledge of this enigmatic planet, but also deepens our comprehension of planetary formation and atmospheric dynamics across the cosmos. The study of these dark worlds opens a fascinating window into the mysteries of the universe. TRES 2b is often celebrated as the darkest exoplanet discovered so far, absorbing an astonishing 97% of the light that hits it. The planet's strikingly low albedo, a measurement of how much light its surface reflects, can primarily be attributed to its unique atmospheric composition. This remarkable absorption is believed to result from an atmospheric blend of various chemicals and phenomena that enhance its dark appearance. One of the significant contributors to TRES 2b's incredibly low reflectivity is the presence of clouds composed of sodium and potassium. These elements, when suspended in the atmosphere, can absorb visible light effectively, which further diminishes the planet's luminosity. This is not unlike how certain materials on Earth can appear darker when they have a high concentration of specific compounds. Additionally, the atmosphere of TRES 2b is thought to contain significant amounts of carbon, which can form complex compounds that also contribute to the planet's light-absorbing qualities. This dark cloud cover, combined with the intense heat, more than 1,000 degrees Fahrenheit, causes any potential light to dissipate rapidly, leaving behind a stark and enigmatic celestial body that challenges our understanding of planetary atmospheres. As researchers continue to study TRES 2b, they also explore how atmospheric dynamics play a role in its low albedo. The interplay between temperature, composition, and pressure can create conditions that favor the retention of these dark materials, revealing not only the uniqueness of this exoplanet, but also the complexities of atmospheric science in our quest to understand the diverse environments of the universe. TRES 2b is a fascinating planet located about 77 light-years away from Earth in the constellation Draco. What sets this exoplanet apart is its remarkable darkness. It is known as one of the darkest planets ever discovered. In fact, it reflects less than 1% of the light that hits it, which gives it an appearance darker than that of coal. This unique characteristic has profound implications for astronomers trying to observe and study the planet. The low reflectivity of TRES 2b presents significant challenges for observational techniques. Traditional methods typically rely on reflected starlight to glean details about a planet's atmosphere and surface conditions. However, with TRES 2b, the scant light that it does reflect makes it difficult for scientists to gather the necessary data to understand its composition and environment. This means that astronomers must often turn to other techniques, such as direct imaging or studying the planet's transit across its host star to gather insights about TRES 2b. Additionally, the planet's unique makeup contributes to its overall thermal characteristics. TRES 2b orbits very close to its star, resulting in extreme temperatures that can exceed 1,000 degrees Celsius. This intense heat causes atmospheric elements to behave differently than those in cooler environments, influencing what scientists can detect. As a result, astronomers must take into account not just the darkness of the planet, but also its fiery atmosphere when interpreting the data they collect. The combination of darkness and extreme conditions of TRES 2b pushes the boundaries of our observational capabilities. Scientists continue to explore advanced technologies and methodologies to unlock more secrets of this enigmatic planet. Each new piece of information adds depth to our understanding of exoplanets and ignites curiosity about the diversity of worlds beyond our own. As research progresses, the study of TRES 2b not only challenges our existing techniques, but also enriches our appreciation for the vast cosmos in which we reside. Detecting planets that reflect minimal light presents a unique set of challenges for scientists. Most of the techniques used in the search for exoplanets, or planets outside our solar system, rely on capturing the faint light those bodies emit or reflect. When a planet is particularly dim and reflects little light, it becomes exceedingly hard to distinguish it from the vast backdrop of stars and cosmic noise surrounding it. One of the primary methods for discovering exoplanets is through the transit method, which involves observing the slight dimming of a star's light when a planet passes in front of it. However, if a planet reflects very little light, the drop in brightness might be difficult to detect amid the fluctuations caused by other factors, such as stellar activity or the presence of other celestial bodies. The precision required to measure such tiny changes in brightness is immense, often requiring advanced technology and techniques. Additionally, the distance of these planets from Earth adds another layer of complexity. The farther away a planet is, the more its light becomes diluted, making it harder to spot through traditional telescopes. This is particularly true for planets located around dim stars, known as red dwarfs, which can complicate the identification process further. It requires a combination of multiple observations over time to build enough evidence for existence, which can be both time-consuming and resource-intensive. Moreover, scientists must also grapple with atmospheric interference. The Earth's atmosphere can skew observations, often obscuring faint light signatures. To counter this, astronomers may use telescopes located high in the atmosphere or even in space, where they are free from atmospheric disturbances. Sophisticated algorithms and computer models are then employed to differentiate between real planetary signals and background noise, ensuring that even the faintest reflections do not go unnoticed. In overcoming these challenges, scientists continue to push the boundaries of our understanding of the cosmos, expanding the list of known worlds that share our universe. TRES 2b is a fascinating exoplanet, often described as the darkest known planet. Located nearly 1,000 light-years away in the constellation Draco, it reflects less than 1% of sunlight that reaches it. Such an extreme level of darkness raises important questions about the atmospheric composition of this distant world. The characteristics that give TRES 2b its unique appearance likely involve complex interactions of molecules within its atmosphere. Scientists suggest that this planet's atmosphere might contain light-absorbing chemicals like gases, clouds, or perhaps even a mix of condensed materials. Understanding the properties of TRES 2b not only provides insights into its composition, but also gives clues about how atmospheres can vary across different planetary environments. By studying TRES 2b and similar exoplanets, we learn more about the ways atmospheres influence surface temperatures and weather patterns. For instance, a darker planet may indicate an inefficient heat absorption, potentially leading to extreme temperatures and weather systems unlike those found on Earth. In comparison, knowing that higher reflectivity often corresponds with cooler environments allows researchers to hypothesize about diverse climates across the universe. These findings serve as a stepping stone toward broader implications for our understanding of planetary development. They encourage us to consider how diverse atmospheric compositions might lead to varying evolutionary paths for different planets. Grasping the significance of a planet's darkness, like that of TRES 2b, deepens our appreciation for the incredible variety that exists beyond our solar system and enriches our search for potentially habitable worlds. The discovery and analysis of planets that exhibit unusual reflective properties heavily rely on advanced telescopes, both ground-based and space-based. These telescopes equipped with sophisticated instruments can capture the faint light emitted or reflected by distant celestial bodies. One notable example is the Hubble Space Telescope, which allows astronomers to observe distant exoplanets in remarkable detail, providing vital data on their atmospheric composition. These observations are crucial because the way a planet reflects light can reveal much about its surface and atmospheric conditions. One of the most fascinating tools used in this exploration is the technique known as spectroscopy. By splitting light from a planet into its constituent colors, scientists can identify specific wavelengths that are absorbed or emitted by different elements and compounds. This method helps determine the chemical makeup of a planet's atmosphere, including the presence of gases that may indicate conditions suitable for life. For example, the detection of reflective clouds or hazes in an exoplanet's atmosphere can suggest its weather patterns and potential habitability. In recent years, advances in technology have introduced new instruments like transit photometry, which observes the light variations when a planet passes in front of a star. This technique allows for the measurement of a planet's size, mass, and distance from its host star. It also provides insight into the planet's reflective properties, which can change dramatically depending on the materials that make up its surface and atmosphere. As telescopes and instruments become more refined, astronomers can uncover the secrets behind these enigmatic worlds. Moreover, the next generation of telescopes, including the James Webb Space Telescope, promises even deeper insights. With its ability to observe in infrared wavelengths, astronomers will unlock new details about the atmospheres of far-off planets. Such discoveries will not only enhance our understanding of the universe, but also potentially guide us toward finding Earth-like conditions elsewhere, sparking curiosity about what life may exist beyond our solar system. As we look to the future of astronomical exploration, missions dedicated to studying dark exoplanets like TRES-2b open the door to groundbreaking discoveries. TRES-2b, known as one of the darkest planets ever observed, reflects less than 1% of the light that strikes its surface. Understanding such celestial bodies is essential because it challenges our knowledge of planetary formation, atmospheric composition, and the conditions that might exist in these distant worlds. Future missions will likely employ advanced observational technologies capable of detecting the subtle signals emitted by these enigmatic planets. For example, space telescopes equipped with enhanced spectrometers will allow scientists to analyze light as it passes through a planet's atmosphere. This tool can reveal the chemical composition of these atmospheres and provide insights into their physical properties. By identifying the gases present, researchers might better understand not only the planet's surface conditions, but also its potential for hosting life or its environmental dynamics. Additionally, missions designed to observe transits, events when a planet passes in front of its host star, will improve our ability to characterize dark exoplanets. By monitoring the tiny dips in starlight caused by these transits, scientists can infer vital information about the size, orbit, and even temperature of these planets. Innovations in telescope technology, such as the use of more sensitive detectors and adaptive optics to correct for atmospheric distortions, will enhance these observations, allowing us to paint a clearer picture of these mysterious worlds. Moreover, the exploration of dark exoplanets could reveal surprising interactions between them and their host stars. Studies focused on how planetary atmospheres respond to stellar radiation and how that process influences their darkness could help scientists refine their theories about planet formation and evolution. In coming years, through daring missions and sophisticated technology, our understanding of dark exoplanets like TRES-2b may just illuminate the shadows of our cosmic knowledge. TRES-2b, known as one of the darkest exoplanets, reflects less than 1% of the light that hits it. This extraordinary level of darkness raises questions about the elements that might contribute to its shadowy nature. Natural satellites and rings could potentially play a significant role in enhancing the darkness we observe from afar. First, let's consider a scenario where TRES-2b has a natural satellite. If this moon were to orbit close enough, it might influence the light scattering on the planet's surface. The gravitational pull from the satellite could lead to tidal heating, possibly generating geological activity that exposes darker materials. If volcanic eruptions or other processes bring forth carbon-rich compounds, they could further absorb light instead of reflecting it, thereby boosting the planet's overall darkness. Next, Rings surrounding TRES 2b could similarly impact its apparent darkness. Rings composed of tiny dark particles could absorb sunlight before it reaches the planet. Any light that manages to slip through the ring system could easily be absorbed or scattered by the planet's unique atmosphere, which is already proficient at swallowing light due to its composition. This interplay of interference with light means that ring systems could contribute to an even deeper shade of blackness. Moreover, the presence of both a satellite and rings could influence weather patterns and climate on TRES 2b. This may create dynamic atmospheric effects that alter how light interacts with the planet's environment. Overall, while TRES 2b is already a remarkable sight in the cosmos, the additional complexities introduced by natural satellites and rings present fascinating possibilities in understanding the various ways celestial bodies can contribute to the shades of darkness we observe. TRES 2b is a fascinating exoplanet that captivates both scientists and the general public for a variety of reasons. Discovered in 2006, it orbits a distant star about 63 light-years away in the constellation Draco. What makes TRES 2b stand out among the plethora of known exoplanets is its astonishingly dark atmosphere. In fact, it is considered the darkest exoplanet ever discovered, reflecting less than 1% of the sunlight that falls upon it. This extreme lack of reflectivity makes it appear almost black, a stark contrast to the shimmering gases of many other planets. The implications of TRES 2b's unusual properties stir excitement in scientific circles. Researchers are eager to understand the unique atmospheric conditions that allow for such a low level of light reflection. This curiosity extends to the composition of the planet's atmosphere, which is believed to be made up of gases like sodium and potassium. These elements not only contribute to its darkness, but could also reveal new insights into the formation and evolution of planetary bodies. Such research helps us gain a deeper understanding of how various planetary environments can differ, even within the same galaxy. For the general public, TRES 2b serves as a window into the diverse possibilities of worlds beyond our own. It raises questions about what life might look like on such an unimaginably dark planet and sparks imagination about extraterrestrial environments. The awe that comes from considering how planets can exist in states vastly different from Earth is understandably captivating. Media coverage often highlights this strangeness, appealing to our innate curiosity about the universe and our place within it. Ultimately, TRES 2b ignites wonder not just for its scientific implications, but also for the sheer mystery it holds. The planet challenges our perceptions of what a planet can be, encouraging continued exploration and debate within the scientific community and among the public alike. As we push the boundaries of our understanding of distant worlds, TRES 2b stands as a testament to the incredible variety of the cosmos, inviting us to ponder what other surprises await in the vast expanse of space. Corot 7b is an intriguing exoplanet, orbiting a star located approximately 550 light-years away from Earth. Its extraordinary features primarily stem from its close proximity to its host star, which significantly affects its surface conditions and geological processes. The intense stellar radiation and gravitational forces experienced on Corot 7b create an environment ripe for extreme volcanic activity, transforming this distant world into a fiery landscape. One of the critical contributors to Corot 7b's volcanic nature is its tidal heating. This phenomenon occurs as the planet is subject to the changing gravitational forces exerted by its star. As Corot 7b orbits in a tight and fast orbit, the gravity from the star pulls on the planet unevenly, causing its shape to stretch and flex. This continual flexing generates substantial internal friction, which in turn creates enough heat to melt rock beneath the surface. The result is a dynamic and active volcanic system, akin to some of the volcanic activity seen on Jupiter's moon Io. Furthermore, the composition of Corot 7b plays a significant role in its geological processes. Studies suggest that it is likely a rocky planet, similar to Earth, but with substantial differences, like a thick atmosphere potentially filled with volcanic gases. This atmosphere can be laden with sulfur dioxide and other components released during volcanic eruptions. Such gases can lead to a greenhouse effect, trapping heat and further intensifying volcanic activity. In this brutal environment, Eruptive events may be not only frequent but also incredibly violent. The combination of tidal heating and a volatile atmosphere indicates that Korot 7b is a world of fire and fury. Its relentless volcanic eruptions provide scientists with exciting opportunities to study extreme environments and understand more about planetary formation and geological evolution in other star systems. This exoplanet serves as a fiery reminder of the diverse and dynamic nature of the universe beyond our own blue planet. Korot 7b is a fascinating exoplanet, particularly due to its intriguing volcanic activity, which is closely tied to its interaction with its host star. Located approximately 430 light-years away in the constellation Monoceros, Korot 7b orbits its star at an astonishingly close distance, completing a full orbit in just about 20 hours. This proximity leads to significant tidal forces exerted on the planet, impacting its geological composition and surface features. These tidal forces, a result of gravitational interaction, create considerable stress on Korot 7b's interior. As the planet rotates, the gravitational pull from its star causes the shape of the planet to slightly distort. This constant squeezing and stretching of the planet can generate heat deep within its core, much like how friction ignites a spark. This internal heating can trigger volcanic activity, leading to the release of lava and gaseous materials onto the surface. Furthermore, the continuous tidal heating on Korot 7b has likely shaped its very landscape. The heat produced not only fosters volcanoes, but may also contribute to a dynamic environment where molten rock can flow, cool, and reshape the surface over time. It's almost as if the planet is continually reworking itself, creating a striking volcanic terrain that would be breathtaking and violent. This volcanic landscape, influenced by tidal interactions, provides scientists with valuable insights into planetary formation and dynamics. By studying these processes on Korot 7b, astronomers expand their understanding of how similar exoplanets might behave, revealing the broader and varied universe of planetary systems beyond our own. The dynamic nature of Korot 7b not only showcases the wonders of cosmic interactions, but also captivates our imagination about what else lies within the reaches of space. Korot 7b is a fascinating exoplanet that has garnered significant attention due to its volcanic activity. This planet, located about 600 light-years away from Earth, is classified as a rocky exoplanet. What sets it apart is its proximity to its host star, which exposes it to intense heat, likely causing an environment where volcanoes are actively reshaping its surface. Studying Korot 7b's volcanism provides key insights into the geological processes that may occur on similar rocky planets in different solar systems. Volcanism on Korot 7b offers a unique glimpse into the inner workings of exoplanets. Given its molten surface, scientists utilize observations of this planet to understand how heat influences geological features. This includes exploring how volcanic eruptions may affect atmospheric conditions, which could have far-reaching implications for habitability. By investigating these volcanic processes, researchers can create models that help predict the behavior of other rocky exoplanets in various cosmic environments. Furthermore, the study of volcanic activity on Korot 7b helps scientists draw parallels between exoplanets and the geological history of Earth. The characteristics of this planet's volcanism can reveal fundamental principles about planet formation and evolution. For instance, understanding how extreme conditions can lead to significant geological change gives us insight into the physical limits of rocky planets, possibly even reshaping our criteria for what makes a planet habitable. In a broader sense, researching Korot 7b and its volcanoes enriches our comprehension of the diversity of planetary systems in our galaxy. With thousands of exoplanets detected, each with their own unique characteristics, examining volcanic activity on planets like Korot 7b enhances our understanding of the complex interplay between geology, atmosphere, and potential life beyond our own world. As we continue to unravel the mysteries of such exoplanets, we edge closer to understanding the full tapestry of the universe's rocky planets. Monitoring volcanic activity on distant exoplanets such as Korot 7b requires a combination of advanced technology and innovative techniques. Since these planets are located light-years away, direct observation is nearly impossible. Instead, astronomers rely on telescopes equipped with sophisticated instruments to gather information about their atmospheric and surface conditions. One key piece of equipment is the space-based telescope. These telescopes, like the Kepler and TESS missions, are designed to detect transient signals from planets as they pass in front of their host stars. This transit method can reveal changes in a planet's brightness, which may indicate volcanic activity. Infrared telescopes are particularly useful as they can identify heat emitted by volcanic eruptions, allowing scientists to discern if there are active lava flows or other geological processes. Spectroscopy is another critical technology for this monitoring. By analyzing the light spectrum from a planet's atmosphere, scientists can detect the presence of specific gases often associated with volcanic activity, such as sulfur dioxide. These atmospheric signatures can provide insights into the chemical processes occurring on the planet's surface. With potential future missions that will include more sensitive instruments, we may even be able to observe real-time volcanic events. Finally, computer modeling plays a vital role in understanding the data collected. By simulating volcanic eruptions and the resulting atmospheric changes, researchers can predict how these phenomena would appear to distant telescopes. As technology evolves, the combination of advanced telescopes, sophisticated spectroscopy, and powerful computational methods will enhance our ability to monitor volcanic activity not just on Corot 7b, but also across a range of distant worlds. Through these methods, we edge closer to unlocking the mysteries of volcanic activity on alien planets. Corot 7b, discovered in the year 2009, stands out as an intriguing exoplanet located about 600 light-years from Earth. This distant world is classified as a rocky planet, similar in composition to our own Earth. However, what makes Corot 7b particularly fascinating is its extreme conditions. It orbits its host star, a type of red dwarf, much closer than the planets in our own solar system due to the Sun. As a result, Corot 7b experiences intense heat, leading to a surface that may be characterized by extensive volcanic activity. The discovery of Corot 7b has provided scientists with a unique laboratory to study what volcanic activity looks like on a planet outside our solar system. The planet's high surface temperatures reach levels sufficient to melt rock, and evidence suggests that this molten state could lead to lava flows and volcanic eruptions. Researchers have found that the size and mass of Corot 7b indicate it likely retains considerable heat from its formation, which could drive ongoing volcanic processes. Moreover, observations have indicated the presence of certain minerals in the planet's atmosphere, possibly created by volcanic outgassing. This technique helps scientists deduce not only the planet's geological activity, but also its potential for atmospheric interactions that mirror processes seen on Earth and other rocky planets. By studying such volcanic activity, astronomers can glean important insights into the geological evolution of planets around stars other than our own, enhancing our understanding of planetary formation and development across the universe. Ultimately, Corot 7b serves as a vital piece of the cosmic puzzle, allowing scientists to explore the dynamics between stellar radiation and volcanic activity. This research fuels the quest to identify habitable worlds beyond Earth, prompting questions about how varied conditions on other planets may shape their atmospheres and, more intriguingly, the potential for life. Through these explorations, we gain a deeper appreciation of the diverse environments that exist in the universe, expanding our understanding of what governs the very nature of planets. Volcanic eruptions on Earth are fascinating phenomena that showcase the intricate dance between our planet's geology and atmosphere. Earth's eruptions typically involve the expulsion of molten rock, gases, and ash from deep within the planet's mantle through volcanic vents. The type of eruption can vary widely, from gentle lava flows to explosive blasts, influenced by the composition of the magma and the pressure buildup beneath the surface. Additionally, Earth's atmosphere plays a vital role, as wind can carry ash across vast distances, impacting environments and human activities far from the eruption site. In contrast, the predicted volcanic eruptions on Corot 7b present a strikingly different picture. This exoplanet, located outside our solar system, is primarily rocky but orbits very close to its star, resulting in starkly different conditions. Corot 7b is tidally locked, meaning one side perpetually faces the star while the other remains in darkness. This extreme temperature difference creates intense heat on the star side, leading to unique volcanic activity likely dominated by lava oozing from volcanic cracks, rather than explosive eruptions as we typically witness on Earth. Moreover, the atmosphere of CoRoT 7b, if it exists, could be vastly different from Earth's, affecting how gases are emitted during eruptions. The thick, superheated gases could create an environment unsuitable for the types of eruptions found on our planet. Instead of ash clouds soaring into a breathable atmosphere, the eruptions on CoRoT 7b may release molten rock that cools rapidly in the intense stellar heat, or forms volcanic pits that brim with molten lava, contributing to a landscape entirely unlike what we know. Ultimately, while both Earth and CoRoT 7b share volcanic roots, their eruptions are tailored to their distinct environments. The combination of gravitational forces, geological composition, and variable thermal conditions results in eruptions that are fundamentally different in behavior and impact, inviting us to marvel at the diversity of volcanic activity across the universe. CoRoT 7b is a fascinating exoplanet located about 400 light-years from Earth, orbiting its star in the constellation of Monoceros. Discovered in 2009 by the CoRoT Space Telescope, this celestial body has intrigued astronomers due to its unusual characteristics. CoRoT 7b is classified as a super-Earth, a type of exoplanet significantly larger than Earth but smaller than Neptune. One of its most striking features is its volatile surface, rich in elements that suggest extreme environmental conditions. Astronomers believe that the formation of CoRoT 7b's volatile surface can be traced back to its close proximity to its host star. The planet orbits at an extraordinary speed, completing a full orbit in just over 20 hours. This rapid orbit places CoRoT 7b in an environment with extreme temperatures, potentially exceeding 1,000 degrees Celsius on its sunlit side. Such scorching conditions can drive atmospheric elements, including volcanic gases, away from the surface. The theories surrounding this volatile landscape suggest that CoRoT 7b may experience significant volcanic activity. Its surface could be covered with molten rock, constantly reshaped by erupting volcanoes that release volatile compounds such as sulfur and various gases. This ongoing geological activity plays a vital role in maintaining the planet's dynamic atmosphere, even in the face of extreme heat. The interaction between the atmosphere and the rocky surface could lead to the formation of unique mineral structures unlike those found on Earth. Moreover, the composition of CoRoT 7b is crucial for understanding its evolutionary history. Studies indicate that it contains a substantial amount of metals and silicates, hinting at a complex formation process influenced by its parent star's radiation and gravitational pull. As scientists gather more data about this intriguing planet, they continue to refine their models and deepen our understanding of planetary systems, both familiar and far beyond our own. CoRoT 7b serves as a reminder of the incredible diversity and complexity of worlds that exist in our universe. The planet CoRoT 7b, part of a system approximately 600 light-years from Earth, presents a fascinating case for scientists studying exoplanet atmospheres and geology. This rocky world is unique due to its close proximity to its parent star, leading to extreme temperatures and conditions that significantly influence its surface and atmospheric composition. The composition of an exoplanet's atmosphere can dictate not only its climate, but also its geological activity, particularly volcanic eruptions. In the case of CoRoT 7b, the intense heat from its star is critical. The surface temperature can soar higher than 1,000 degrees Celsius. Such extreme heat leads to the possibility of a molten surface and a sky filled with vapors from various elements, including vaporized rock and metals. This extreme environment can facilitate sustained volcanic activity. The volcanic eruptions on CoRoT 7b likely serve as a critical mechanism for releasing gases from the planet's interior, contributing to its atmospheric composition and maintaining its geologically active state. Moreover, the atmosphere may be rich in substances like potassium, sodium, and other minerals. The presence of these materials, along with the intense thermal energy from its star, can create conditions ripe for ongoing volcanic eruptions. This continuous geological activity can, in turn, recycle materials from the surface back into the atmosphere, creating a dynamic interplay between volcanic processes and atmospheric evolution. Understanding the role of atmospheric composition on CoRoT 7b helps scientists draw parallels with our own planet and others in the universe. By analyzing the processes that sustain volcanic activity in such an extreme environment, researchers gain insights not only into the history and development of this distant world, but also into the nature of planetary systems outside our own. This research has broader implications for understanding how atmospheres form and evolve, particularly in challenging environments. The exoplanet Corot 7b has captured the attention of scientists not only for its unique characteristics, but also for its intriguing volcanic activity. Located about 430 light-years away in the constellation of Monoceros, this rocky planet is known for extreme temperatures and a close orbit around its host star, leading to intense volcanic eruptions. By studying these volcanic processes on Corot 7b, researchers can gain valuable insights that may enhance our understanding of volcanism here on Earth. Corot 7b orbits its star in just 20 hours, resulting in a surface hot enough to melt rock. This extreme environment contrasts sharply with Earth's more temperate conditions, offering a unique perspective on the mechanics of volcanic activity. For instance, the heat from the star may create conditions that drive different volcanic processes, including how magma forms and transports to the surface. Observing these processes can help scientists identify what influences volcanic eruptions on rocky planets, including the relationship between temperature, pressure, and planetary composition. Furthermore, studying the volcanic activity on Corot 7b could illuminate the role of tectonic movements in shaping a planet's surface. Earth's volcanism is closely linked to plate tectonics, with shifting plates triggering eruptions and the formation of new geological features. Analyzing the volcanic features on Corot 7b might reveal whether similar processes are at work or if entirely different mechanisms dominate, potentially leading to new theories about how rocky planets evolve. Examining the volcanoes of Corot 7b allows scientists to extend their thinking beyond our planet's unique conditions. By comparing volcanic activity across different environments, researchers can develop a more comprehensive view of not only our own volcanic systems, but also the diverse geological processes operating throughout the universe. Each new discovery on planets like Corot 7b adds another layer of depth to our understanding of planetary science, broadening the horizon of how we view volcanism, both on Earth and beyond. Corot 7b has emerged as a significant object of study in the field of exoplanets, not just for its unique features, but also for what it reveals about the variety of planetary environments beyond our solar system. Discovered in 2009 by the French space mission Corot, this exoplanet orbits a star located over 400 light-years from Earth. What makes Corot 7b particularly fascinating is its classification as a super-Earth, a type of planet that is larger than Earth but smaller than Neptune. One of the most compelling aspects of Corot 7b is its extreme surface conditions. It is located very close to its host star, which means it experiences intense heat and radiation, leading to significant atmospheric variations. This proximity to its star results in a surface temperature hot enough to melt rocks, with estimates suggesting temperatures that may exceed 1,000 degrees Celsius. Such extreme environments challenge our understanding of planetary formation and the potential for life in radically different conditions compared to our own planet. Researchers are particularly captivated by the planet's potential for volcanic activity. The heat from its star may lead to active geology, possibly resulting in ongoing volcanic outgassing. This phenomenon makes Corot 7b a vital subject for understanding the dynamics of rocky exoplanets under extreme conditions. These insights can help us piece together the geological history of similar planets, as well as their atmospheric compositions, which might be drastically different from what we observe on Earth. Furthermore, studying Corot 7b contributes to the broader conversation about planetary habitability. The extreme conditions raise questions about whether other planets orbiting close to their stars might harbor environments that are hostile to life as we know it, but could still support life forms adapted to such extremes. As scientists uncover more about Corot 7b, they continue to refine their models of planetary systems, setting the stage for future explorations and discoveries throughout the cosmos. Cancri E has captured the imagination of scientists and enthusiasts alike, earning itself the catchy nickname Diamond Planet. This fascinating exoplanet, located about 40 light-years away in the constellation Cancer, stands out due to its unique composition and structure. Its most intriguing feature is the high concentration of carbon, which, under the right conditions, suggests that the planet may possess a substantial amount of diamond beneath its surface. Researchers believe that 55 Cancri E is primarily made of carbon and has a particularly thick atmosphere rich in elements like hydrogen and helium. The planet's extreme temperatures, which can reach nearly 2,700 degrees Fahrenheit, contribute to this unusual makeup. At such high temperatures and pressures, carbon can transform into diamonds, creating the poetic idea of a planet glittering with precious stones. This planet orbits its star in just about 18 hours, resulting in a year that lasts less than a day. It is tidally locked, meaning one side faces its star constantly while the other remains in darkness. This stark contrast in environmental conditions further influences its physical characteristics, and scientists hypothesize that the dark side might have conditions favorable for diamond formation due to the intense pressure and temperature. The prospect of mining diamonds on 55 Cancri E, while intriguing, remains firmly in the realm of fantasy. To reach this exotic world would require technology far beyond our current capabilities. However, the sheer existence of such a planet fuels our curiosity about the universe and the vast array of planetary possibilities that reside within it, reminding us just how extraordinary our cosmos is. 55 Cancri E, located 40 light-years away in the constellation Cancer, is a fascinating exoplanet that challenges our understanding of what rocky planets can be. Unlike Earth and other familiar rocky celestial bodies, this planet's chemical composition and surface conditions are strikingly different. While rocky planets in our solar system are primarily composed of silicate minerals and metals, 55 Cancri E is believed to have a unique blend of materials that includes a significant amount of carbon, with hypotheses suggesting that it could even have a surface rich in graphite and diamonds. The extreme conditions on 55 Cancri E are largely attributed to its proximity to its host star, which is a little bit cooler than our Sun, but still exerts an enormous amount of heat on the planet. This results in surface temperatures that can soar to over 2,000 degrees Fahrenheit. Such high temperatures are quite unlike those on Earth, where we enjoy a more temperate climate conducive to life. Instead of oceans or lakes, 55 Cancri E may have a molten surface, or perhaps even vast expanses of lava shaped by the intense heat. Additionally, the atmospheric conditions are drastically different on this planet. While Earth has a balanced atmosphere composed of nitrogen and oxygen that supports life, 55 Cancri E appears to have a thick, toxic atmosphere laden with steam, carbon monoxide, and possibly hydrogen. This dense air would create an oppressive environment, making it inhospitable to life as we know it. The pressure on this planet would also be much higher than on Earth, potentially leading to unique geological and atmospheric phenomena. 55 Cancri E stands as a remarkable example of how diverse planetary environments can be. Its unique chemistry, extreme temperatures, and hostile atmospheric conditions differentiate it profoundly from traditional rocky planets like our own. This exoplanet serves as a reminder of the vast possibilities that exist beyond our solar system, expanding our understanding of what constitutes a planet and challenging our assumptions about their potential for habitability. The formation of carbon-based minerals such as diamond on a planet involves a complex interplay of geological processes that take place over millions of years. At the heart of this process is carbon itself, which is the fourth most abundant element in the universe. It typically enters a planet's geology through a variety of sources, including volcanic eruptions, organic matter, and even the remnants of ancient stars. Once on the planet, carbon undergoes specific conditions that could transform it into diamonds. One primary process occurs deep within a planet's mantle, where intense heat and pressure are abundant. Under these conditions, carbon atoms begin to bond in a specific arrangement, forming a crystal structure that characterizes diamonds. This process can take place in regions where tectonic activity is prevalent, leading to the movement of carbon-rich materials from the surface down into the depths of the mantle. As the pressures exceed approximately 725,000 pounds per square inch, existing carbon can crystallize into diamonds, producing a treasure trove of gems beneath the surface. Another fascinating aspect involves the impact of meteorites. When meteorites collide with a planet's surface, the sheer force of the impact can create the extreme temperatures and pressures necessary for the formation of diamonds. This is seen, for example, on Earth, where meteorite impact sites have been found to contain microdiamonds formed during such high-energy events. These occurrences are rare, but are crucial for understanding how diamonds can be naturally produced under extraordinary circumstances. Lastly, the presence of carbon-rich substances, such as decaying biological materials, can also lead to diamond formation over geological timescales. In environments where carbon is abundant, specific conditions can facilitate the transformation of this carbon into diamonds through processes like metamorphism, where heat and pressure gradually reshape carbon-rich rocks. Thus, the formation of diamonds does not rely solely on one process, but rather a combination of various geological and cosmic events that together contribute to a planet's carbon wealth. Scientists have developed sophisticated methods to gain insights into a planet's interior without ever having to drill down or send probes directly into its depths. One of the primary tools at their disposal is the study of seismic waves, which are generated by natural events like earthquakes or man-made explosions. These waves travel through the planet's interior and can provide crucial information about its composition and structure. By analyzing how these waves change speed and direction as they pass through different materials, scientists can infer what lies beneath the surface. Another vital method involves studying a planet's gravitational and magnetic fields. Through sophisticated measurements, scientists can detect slight variations in gravity that hint at the density of different materials below the surface. For instance, if an area of a planet shows a stronger gravitational pull, it may indicate the presence of denser materials, such as metals, while a weaker gravitational field might suggest less dense components, like silicates. Similarly, variations in magnetic fields can reveal insights about the planet's core and its geological history. Temperature and pressure also play significant roles in understanding a planet's interior. Scientists can simulate the extreme conditions of deep planetary interiors in the lab and observe how materials behave under those conditions. By combining this experimental data with models of planetary formation and evolution, researchers can make educated predictions about a planet's internal structure and composition. By utilizing these methods and technologies, scientists can piece together a picture of a planet's interior with remarkable accuracy. It is a testament to human ingenuity that we can uncover the secrets of worlds beyond our own without needing to set foot on them. The combination of seismic studies, gravitational mapping, and experimental simulations allows researchers to not just understand our own planet, but also extends to others in our solar system and beyond. 55 Cancri E is a fascinating exoplanet located about 40 light-years away from Earth, orbiting a star in the constellation Cancer. Its unique characteristics make it a prime candidate for future missions focused on exotic minerals. This planet is classified as a super-Earth, and its size is approximately twice that of our own world. Remarkably, it has a surface temperature that exceeds 1,300 degrees Fahrenheit, indicating an incredibly hostile environment. One of the most intriguing aspects of 55 Cancri E is its composition. Scientists believe it is largely made up of carbon, which could potentially mean the presence of diamonds and graphite in its crust. In fact, some estimates suggest that a significant portion of this planet's mass could be in the form of diamond. The prospect of mining such exotic minerals raises not only scientific curiosity, but also economic excitement. Imagine the implications of having access to vast resources of diamonds far beyond what we find on Earth. Additionally, this exoplanet holds unique geological features. Its extreme conditions, influenced by its close orbit to its parent star, create an environment that could sustain various forms of mineralization not found within our solar system. The possibility of discovering new types of materials and their properties holds immense potential for advances in technology and industry. Missions focused on exploring 55 Cancri E could unveil secrets of exotic minerals that could revolutionize material science. As we develop the technology necessary for distant exploration, 55 Cancri E stands out as a beacon of possibilities. Further studies could provide invaluable insights into not just the composition of this super-Earth, but also about planetary formation and the evolution of worlds under extreme conditions. The allure of exotic minerals combined with the marvel of understanding our universe makes 55 Cancri E an exciting frontier in the field of astrobiology and materials science. The intriguing planet known as 55 Cancri E is often referred to as a diamond planet due to the significant presence of carbon, which may exist in the form of diamond under its extreme conditions. This exoplanet is located approximately 40 light-years from Earth and is notably larger and denser than our own planet. The influence of diamonds on geological activity here is a fascinating topic that combines chemistry and geology in a new light. Diamonds form under extreme pressure and temperature conditions, and on 55 Cancri E, the environment is thought to be particularly inhospitable, with surface temperatures soaring to around 2,000 degrees Fahrenheit. If diamonds are indeed abundant in its crust and mantle, their presence could influence volcanic activity and tectonic movements. Diamonds, being stable structures, may inhibit certain geological processes, potentially leading to a lack of traditional volcanic eruptions. Conversely, the presence of carbon in other forms, such as graphite or even supercritical carbon dioxide, could result in unique geological features. Unlike Earth, where the movement of tectonic plates creates mountains and valleys, the geological activity on this planet may involve bursts of carbon and heat resulting from the extreme pressures. Such conditions might create a different landscape altogether, consisting of large diamond reserves rather than typical silicate rock formations. Ultimately, the chemistry and geology of 55 Cancri E, with its potential diamond-rich composition, remain largely speculative, as direct observations are limited. However, this tantalizing possibility helps paint a picture of how alien worlds can differ dramatically from our own, while sparking curiosity about the processes that shape them. The thought that the very ground on this distant planet could be embedded with diamonds opens a new chapter in our understanding of planetary formation and composition beyond our solar system. 55 Cancri E is a fascinating exoplanet located about 40 light-years away from Earth. It is one of the first discovered Earth-sized planets within the habitable zone of its host star, a sun-like star known as 55 Cancri A. What makes this planet particularly intriguing is its nature as a super-Earth, which means it has a mass more than that of Earth, but significantly less than that of gas giants like Neptune. Understanding its interior structure poses unique challenges for scientists and astronomers trying to model this distant world. One of the primary hurdles in modeling the interior of 55 Cancri E is the limited observational data available. Unlike planets in our own solar system, which we have closely studied through missions and telescopes, 55 Cancri E is far beyond our immediate reach. Researchers often rely on indirect observations, such as the planet's size, mass, and the nature of its star's light. These measurements can only provide rough estimates about the composition and structure of its interior, leading to uncertainty in models. Additionally, the extreme conditions present on 55 Cancri E further complicate these models. It is hypothesized that this planet might possess a molten or partially molten surface due to its proximity to its parent star, resulting in unusually high temperatures. As a result, factors like pressure and temperature play a critical role in determining the materials that could exist within the planet. The behavior of these materials under such conditions is still not fully understood and requires advanced geological and physical theories to accurately predict. Moreover, there are various hypotheses about the composition of 55 Cancri E. It may consist of a rocky core surrounded by a thick layer of volatile substances, or even an ocean made primarily of molten rock or a unique mix of materials. Creating a detailed model that captures these possibilities involves intricate calculations and simulations, which are often limited by current technology and our understanding of planetary science. The quest to unravel the secrets of 55 Cancri E challenges scientists to expand their models and perhaps rethink what we know about planetary formation and evolution in our universe. 55 Cancri E is a fascinating exoplanet located about 40 light-years away in the constellation Cancer. It has intrigued scientists since its discovery due to its unique characteristics. This planet is classified as a super-Earth, meaning it is larger than our own planet, but considerably smaller than Neptune. What makes 55 Cancri E particularly notable is its potentially rocky composition and the possibility of a thick atmosphere, challenging our existing models of planetary formation. Traditionally, scientists believed that most solid planets formed from the accumulation of gas and dust in the early solar system. However, 55 Cancri E reveals a more complex narrative. Its unusual high density suggests that it may have a substantial metallic core surrounded by a mantle of rock. Clues from its composition could indicate that the processes leading to the formation of super-Earths might differ significantly from those that created smaller terrestrial planets like Earth or Mars. Moreover, 55 Cancri E's orbit places it very close to its host star, resulting in extreme temperatures and geological processes that we do not observe here in our own solar system. This proximity raises questions about the role of stellar radiation in planet formation and evolution. Understanding how such a planet can develop and maintain its structure despite harsh conditions could help reshape our theories related to planetary atmospheres and surface evolution. The discoveries around 55 Cancri E are pivotal, suggesting that planetary systems can be surprisingly varied, with compositions and attributes that differ greatly from our familiar celestial neighborhood. As we continue to unravel the secrets of this exoplanet, we might find significant new insights about the broader processes at play in the universe, leading us toward a deeper understanding of how diverse planetary systems are formed across the cosmos. 55 Cancri E is a fascinating exoplanet, notable not just for its proximity, located just 40 light-years away, but also for its intriguing characteristics. This world is classified as a super-Earth, boasting a mass about 8 times that of our planet. What makes it particularly captivating are the extreme conditions present there. For instance, 55 Cancri E is believed to be a carbon-rich world, with a fierce atmosphere potentially comprising thick clouds of carbon dioxide and possibly even diamonds. Such unique conditions give scientists a fresh lens through which to explore theories about geology beyond our own Earth. The high temperatures on 55 Cancri E, estimated to exceed 2,000 degrees Fahrenheit, suggest that any surface minerals behave quite differently than here on Earth. Researchers are eager to understand how this extreme heat affects geological processes. For example, would the planet have volcanoes that release diamond rain? Could the surface undergo processes similar to those seen in volcanic regions on Earth, where lava flows reshape the landscape? These considerations open the door to novel geological phenomena that challenge our traditional understanding of rock formation and surface evolution. Moreover, the presence of a dense atmosphere could lead to unique weather patterns, potentially influencing erosion and sediment transport in ways we have yet to fully grasp. Scientists are rethinking how atmospheres might interact with geological processes, especially on planets with extreme conditions like 55 Cancri E. The theories that emerge from studying such worlds have the potential to redefine geological sciences, broadening our comprehension of how materials behave under different astronomical conditions. Additionally, 55 Cancri E raises important questions about planetary formation and composition. Observing this exoplanet can help scientists understand how planets evolve in various stellar environments, particularly those around stars much older than our Sun. Each discovery and theoretical advancement inspires even more questions, fueling our curiosity about the diversity of planets in our universe. As we continue to explore 55 Cancri E, we gain fresh insights into not just its geology, but also the broader mechanisms that govern planetary systems far beyond our own. Carbon plays a fascinating role in the atmospheres of celestial bodies, particularly those that have a significant presence of carbon-bearing compounds. These shards of carbon, often found in the form of tiny particles, can influence both the appearance and reflectivity of planets or moons. When these carbon particles become suspended in the atmosphere, they can scatter light in striking ways, altering how we perceive the planet from afar. On some celestial bodies like Saturn's moon Titan, carbon-rich compounds contribute to the rich, hazy atmosphere. The presence of these particles makes the atmosphere thicker and can give rise to colorful cloud formations. As sunlight filters through this haze, it interacts with the carbon particles, enhancing the overall visual complexity and depth of the atmosphere. This phenomenon can make Titan appear yellowish or even orange to observers, showcasing the intricate connections between atmospheric composition and visual aesthetics. Reflectivity, or albedo, is another critical aspect that can be affected by these carbon shards. When light strikes the carbon particles, it can be absorbed or reflected in various directions. This process can lead to a decrease in overall reflectivity, meaning that the body may absorb more sunlight than it reflects. Over time, this can have implications for surface temperatures and the potential for chemical reactions in the atmosphere. The interplay of these carbon particles has broader implications for understanding atmospheres beyond our own. Studying these phenomena can lend insight into how atmospheres evolve, how they interact with sunlight, and the potential for life in extreme environments. Thus, carbon shards do more than just change the appearance of distant worlds. They open a window to the intricate dynamics of celestial atmospheres and their development over time. Ogle 2005 BLG 390 LB stands out in the vast landscape of exoplanets for being one of the coldest ever discovered. Located approximately 27,000 light-years away, this planet lives in the distant reaches of our galaxy, beyond what most telescopes can see. It orbits a star in the Milky Way's crowded star field, but its intriguing feature is not just its location, it's its unyielding chill. This exoplanet has a surface temperature estimated to be around -237 degrees Celsius. Such extreme cold makes it a frigid world, likely composed mainly of ice and rock. It is in contrast to many other exoplanets, which often have scorching temperatures due to closer proximity to their host stars. The coldness of Ogle 2005 BLG 390 LB prompts scientists to consider the processes that could lead to such low thermal conditions. It highlights the unlikely yet fascinating variety of planetary environments that exist throughout the universe. Moreover, the planet was detected using a method called gravitational microlensing, which occurs when the gravitational field of a massive object bends the light of a more distant object. This technique enables astronomers to identify distant celestial bodies that may otherwise remain hidden. The discovery of Ogle 2005 BLG 390 LB in this way illustrates the cleverness of modern astrophysics and the relentless pursuit of knowledge about our universe. As research on cold exoplanets continues, the existence of worlds like Ogle 2005 BLG 390 LB sparks curiosity. They challenge preconceptions of what makes a planet suitable for life and expand our understanding of planetary formation under different conditions. This cold, distant world serves as a reminder that our universe is filled with an astonishing array of planets, many of which carry secrets just waiting to be uncovered. The distance of a planet from its host star plays a critical role in determining its surface temperatures. In the case of distant planets, the farther they are from their sun-like star, the less energy they receive. For instance, an icy world may be positioned at a distance where the light and warmth from its star hardly reach it, resulting in consistently cold temperatures. Consider planets located in the outer regions of a solar system, such as Neptune or Pluto. These planets dwell far from their sun and receive significantly diminished stellar radiation. As a result, any atmosphere they possess is often frigid, and if conditions are right, they may develop icy surfaces. The chilling effect of this distance means that these celestial bodies often exhibit characteristics similar to frozen realms, lacking the kind of warmth that can support liquid water. Additionally, a planet's atmosphere, or lack thereof, influences how it retains heat. Many distant planets have thin atmospheres, offering minimal insulation against the cold of space. Without a substantial blanket of gases to trap heat, they easily lose warmth during their long nights, leading to an average surface temperature that can plummet to extremes. Distance from a planet's star is a fundamental factor in its thermal characteristics. The interplay between distance, stellar energy input, and atmospheric conditions creates the icy domains found in the far reaches of our solar system and beyond. These frozen worlds remind us of the diverse climates existing within the universe, shaped primarily by their relationship with their stars. In our quest to understand the potential for life beyond Earth, the discovery of extremely cold planets like Ogle 2005 BLG 390 LB opens a fascinating chapter in astrobiology. This distant world, located about 22,000 light-years away, orbits a star with conditions that are frigid by our own standards, existing in an environment where surface temperatures can plummet to around -200 degrees Celsius. These extreme temperatures lead many to question whether such a planet could support any form of life. Scientists have begun to explore the concept of life existing in environments that would seem inhospitable to us. It is essential to recognize that life as we know it thrives on water and warmth, but it does not necessarily follow that all life must adhere to these criteria. Some researchers are investigating the possibility of life forms that are not reliant on the typical chemical reactions we observe on Earth. Hypothetical organisms might survive in an environment such as Ogle 2005 BLG 390 LB, utilizing chemical processes adapted to extreme cold. Moreover, the study of extremophiles, organisms that live in Earth's harshest environments, provides critical insights into this potential. For instance, some microbes can endure freezing temperatures by entering a dormant state, essentially pausing their metabolic activities until conditions improve. This ability suggests that similar mechanisms might enable organisms on cold exoplanets to survive extended periods in frigid climates, waiting for opportunities to thrive if conditions were to change. Through instruments that analyze atmospheres and track planetary conditions, scientists continue to gather data that may reveal whether Ogle 2005 BLG 390 LB or similar planets harbor the building blocks of life. Although our current understanding of life favors warmer, wetter environments, the vast diversity in the universe compels us to expand our imagination. The journey of discovery urges us to look for life in places we would not have considered before. Astronomers have developed a fascinating arsenal of techniques to study distant icy worlds that lie far beyond our solar system. These celestial bodies, which include planets, moons, and comets, often reside in regions too remote for direct observation with conventional telescopes. Instead, astronomers rely on a mix of imaging, spectroscopy, and computer modeling, together creating a clearer picture of these enigmatic objects. One of the primary tools in this exploration is the use of telescopes equipped with advanced imaging technology. Observatories on Earth and in space employ infrared and radio wavelengths, which are particularly effective for peering through cosmic dust and gas that often obscure sightlines. The Hubble Space Telescope, and more recent instruments like the James Webb Space Telescope, allow scientists to capture fine details and spectra of distant icy worlds, revealing information about their composition and temperature, as well as their atmosphere's chemical makeup. Spectroscopy plays a star role in unraveling the mysteries of these icy worlds. By analyzing the light emitted or absorbed by an object, astronomers can determine the elements and molecules present. For instance, the signatures of water ice or methane can tell us about these worlds' surface conditions and potential for hosting life. By examining how light interacts with these objects, astronomers can unravel a plethora of information, from the presence of certain gases to surface temperature variations. Moreover, computer simulations and models complement observational data, allowing scientists to predict how these bodies formed and evolved over billions of years. By simulating conditions that would be present on distant icy worlds, astronomers can test hypotheses about their atmospheres and surfaces. This combination of observational and theoretical tools helps astronomers piece together the intricate puzzle of our universe, offering glimpses into realms that once seemed almost unreachable. Through this ongoing exploration, we not only expand our understanding of distant worlds, but also of our own place in the cosmos. Ogle 2005 BLG 390 LB is an intriguing exoplanet located in the cosmic neighborhood of our galaxy. Discovered in 2005, it orbits a distant star and is classified as a super-Earth, which implies it is significantly larger than our own planet. Situated about 25,000 light-years away, it experiences frigid conditions that raise questions about the nature of its atmosphere, if it possesses one at all. In such a harshly cold environment, the prospect of a sustainable atmosphere becomes a fascinating consideration. One potential scenario involves a thick atmosphere rich in gases such as carbon dioxide. Carbon dioxide can trap heat through a greenhouse effect, albeit less efficiently than on Earth, allowing for a more stable climate beneath the chill. Such atmospheric conditions could lead to the existence of frozen nitrogen or methane, creating a complex interplay of ice and gas that could persist in extreme temperatures. Another possibility is the presence of ammonia in the atmosphere. Ammonia has a freezing point significantly lower than water, meaning it could remain in a gaseous or liquid state even in deep cold. This could create a unique environment where ammonia clouds form and actively shape the weather patterns of this distant world. Such compositions would also suggest a different kind of chemical interplay, which could have far-reaching implications for any potential life forms or biological processes. Moreover, scientists speculate about the planet's interaction with cosmic radiation and the effects of its star on atmospheric retention. A thicker and more dense atmosphere could act as a buffer against the cold, creating pockets of warmth where exotic chemical processes might occur. Ultimately, while the conditions on Ogle 2005 BLG 390 Lb may seem inhospitable at first glance, the possibilities for diverse atmospheric compositions open the door to new understandings about atmospheres in extreme environments across the universe. The discovery of Ogle 2005 BLG 390 Lb has provided significant insights into the thermal dynamics of distant exoplanets, challenging previous assumptions about how these planets interact with their environments. This particular planet, located approximately 26,000 light-years away in the Milky Way, is classified as a super-Earth, having a mass more than 5 times that of our planet. What makes it especially intriguing is its position in the gravitational lensing event observed by the optical gravitational lensing experiment. This technique not only confirmed its existence, but has also opened new avenues for studying the atmospheric properties and thermal characteristics of such distant worlds. Investigations into the thermal dynamics of Ogle 2005 BLG 390 Lb reveal that it orbits its host star at a considerable distance, placing it well outside the traditional habitable zone where liquid water could exist. This distance impacts the energy it receives from its star, which is considerably less than that received by planets like Earth. As a result, models suggest that Ogle 2005 BLG 390 Lb may have a frigid atmosphere, potentially composed of various gases that behave differently under low temperatures. Scientists theorize that the atmosphere could be thick with heavy gases, which might trap heat through greenhouse effects, albeit limited due to its distance from any heat source. Furthermore, this discovery has encouraged researchers to refine their models regarding how distant planets can maintain their thermal dynamics. The findings have led scientists to consider factors such as internal heat generation and the potential for geological activity beneath the surface. For instance, if a planet has enough radioactive decay or residual heat from its formation, it may retain a level of warmth that allows for unique chemical processes and possibly even the existence of life, albeit in a very different form than we know on Earth. Overall, the case of Ogle 2005 BLG 390 Lb highlights the importance of exploring diverse planetary systems and the necessity for robust models that take into account a variety of potential conditions. As we continue to uncover new exoplanets, our understanding of how thermal dynamics function across the universe will evolve, revealing the incredible complexity of planetary systems and the nature of worlds beyond our own. Ogle 2005 BLG 390 Lb is an exoplanet that presents a fascinating challenge to our traditional ideas of what makes a planet habitable. Discovered through gravitational microlensing in 2005, this distant world orbits a star situated roughly 25,000 light-years away in the direction of the center of our galaxy. Its distance from its host star marks it as a unique case in the growing catalogue of exoplanets, particularly because it orbits a star that is much dimmer than our Sun. One of the most striking qualities of Ogle 2005 BLG 390 Lb is its extreme conditions. This planet is classified as a super-Earth, meaning it is significantly larger than Earth but smaller than gas giants like Neptune. More importantly, it is believed to possess a frigid surface temperature, likely far below freezing. This raises important questions about the requirements for habitability, as a planet with such cold temperatures would have a starkly different potential for supporting life as we know it. Traditional concepts often prioritize moderate temperatures that allow for liquid water, a foundational element for life on Earth. Adding to the intrigue, Ogle 2005 BLG 390 Lb resides in a binary star system, which complicates the dynamics of potential habitability even further. The gravitational influences from both stars could lead to significant fluctuations in temperature and atmospheric conditions over time. This unique positioning can hinder the stability that many forms of life require, making it difficult for organisms to adapt or thrive amidst such environmental volatility. Adaptive mechanisms that have evolved on stable planets may not find suitable conditions on Ogle 2005 BLG 390 LB. This exoplanet challenges astronomers and astrobiologists alike to expand their definitions of habitability. It encourages a broader exploration of what life might look like in conditions vastly different from those on Earth. As we continue to explore the cosmos and uncover more about the characteristics of distant worlds like Ogle 2005 BLG 390 LB, we edge closer to understanding the diverse possibilities for life in our universe. The more we learn, the more these discoveries challenge our deeply held assumptions about where and how life might exist beyond our own planet. The frozen nature of certain celestial bodies, particularly those found in the outer solar system like ice-covered moons and distant dwarf planets, opens a fascinating window into the evolutionary paths that planets might take. When we study these icy environments, we gain crucial insights into how life could emerge and survive under extreme conditions, possibly mirroring scenarios on other planets that might have similar ice-covered surfaces. Ice acts as a protective layer, preserving substances beneath it that may be crucial for biological processes. On moons like Europa and Enceladus, which are covered in thick layers of ice, scientists believe there are vast oceans of liquid water beneath. These hidden oceans could create conditions suitable for life, suggesting that as long as liquid water exists, complex biological processes could potentially develop, even in stark and hostile environments. Moreover, the presence of frozen materials can influence planetary atmospheres and chemistry. For example, the interaction between ice and various geological processes might lead to the formation of organic compounds. This interplay of factors hints at parallel paths of evolution among planets. If ice-covered planets can sustain liquid water and organic materials, it raises the possibility of diverse evolutionary outcomes based on unique environmental factors, an essential consideration when searching for life beyond Earth. This frozen aspect compels us to rethink our definitions of habitability and the pathways of evolutionary processes. Some theories posit that life could start in ways entirely different from our Earth-centric views. As we continue to explore these frozen worlds, we move closer to understanding not just our planetary neighborhood, but also the broader universe's potential for life and evolution. Exploration of ice-covered worlds, such as the intriguing exoplanet Ogle 2005 BLG 390 LB, is a fascinating frontier in the quest for understanding our universe. Planned future missions aim to deepen our knowledge of these icy bodies, which may harbor secrets about the potential for life beyond Earth. Instruments and missions are being designed to study the atmospheres, surface conditions, and even the subsurface oceans of similar worlds. One such mission is the James Webb Space Telescope, launched to observe distant galaxies, star formation, and the atmospheres of exoplanets. This telescope will employ its powerful instruments to analyze light from planets like Ogle 2005 BLG 390 LB. By detecting specific wavelengths, scientists hope to gather information on the chemical compositions and potential habitability of these distant worlds. Additionally, missions targeting the outer solar system, such as the Europa Clipper, are designed to examine icy moons like Europa, which is believed to have a subsurface ocean beneath its icy crust. Techniques used in these missions, such as radar and thermal imaging, can offer insights into what conditions might be present on exoplanets shrouded in ice, potentially revealing similar habitability. Moreover, advancements in satellite technology and automated observation techniques will enable astronomers to monitor ice-covered worlds in unprecedented detail. By combining data from various sources, scientists are poised to unlock the mysteries of these alien environments in the search for understanding life's potential across the cosmos. Ogle 2005 BLG 390 LB, discovered in the middle of the 21st century, stands out as a significant example in the field of exoplanet research. This planet is situated a little more than 22,000 light-years away from Earth and orbits a star that is not much different from our Sun. What makes Ogle 2005 BLG 390 LB particularly interesting is that it resides within a region categorized as the super-Earth zone. This category contains planets that are larger than Earth but smaller than Neptune, challenging our understanding of potential habitability. One of the most intriguing aspects of Ogle 2005 BLG 390 Lb is its temperature, which is believed to be extremely low, hovering around -100 degrees Celsius. Such frigid conditions prompt scientists to ponder the various climates that can exist among planets with different atmospheric compositions. The planet's characteristics invite questions regarding its atmosphere, surface conditions, and whether it could sustain any form of life, albeit in a very different way than we experience it here on Earth. This particular exoplanet encourages researchers to further explore the climates of planets outside our solar system. Scientists are delving into how a planet's mass, distance from its star, and atmosphere can dramatically shape its climate and potential for habitability. The continued study of Ogle 2005 BLG 390 Lb and similar planets drives inquiry into the very boundaries of planet climatology. Are there other worlds, albeit distant, that may host unique life forms adapted to extreme environments? As we expand our knowledge of Ogle 2005 BLG 390 Lb, we continually redefine what we understand about planetary climates. Each discovery contributes to a much larger story about the universe and its vast array of worlds. It is through such intriguing findings that the search for extraterrestrial life and understanding of climate possibilities continues to evolve, inspiring both researchers and enthusiasts alike to keep questioning our universe's complex nature. HD 80606b is a gas giant exoplanet located about 95 light-years away from Earth in the constellation Ursa Major. It caught the attention of astronomers due to its highly eccentric orbit. Unlike many planets that follow nearly circular paths around their stars, HD 80606b has an orbit that stretches far from the star and then swings back in a rapid, tight arc. This means that its distance from the star varies drastically, from being extremely far away to coming extraordinarily close. At its closest approach, HD 80606b experiences intense heating, leading to atmospheric conditions that can be described as chaotic. This kind of environment means that the planet undergoes significant temperature fluctuations. When it swings into its closest approach, or periapsis, the planet's temperature can rise to nearly 1,500 degrees Fahrenheit, while it can cool down dramatically as it moves away from the star. This radical difference in temperature can create extreme weather patterns, potentially resulting in high-speed winds and rapid shifts in atmospheric pressure. Another factor contributing to its intrigue is the gravitational influence exerted by the host star, HD 80606. The star itself is a pulsating variable star, which means that its brightness changes over time. These variations can impact the stability of the planet's orbit, leading to potential long-term shifts in its path. This complexity poses questions about how planetary atmospheres can adapt to such extreme conditions over time. Lastly, HD 80606b provides astronomers with a unique opportunity to study planetary atmospheres under varying conditions. Understanding how such an extreme environment operates can shed light on the dynamics of exoplanets, particularly those that share characteristics with gas giants. It raises compelling questions. How do planets like this evolve? What mechanisms are at work in their atmospheres? This chaotic dance of HD 80606b not only challenges our understanding of planetary systems, but also invites deeper inquiry into the mysteries of the universe. HD 80606b is an exoplanet that presents a fascinating example of how orbital eccentricity can dramatically influence surface conditions. This particular planet orbits its star in a highly elongated path, making it one of the most eccentric orbits known among exoplanets. While most planets in our solar system follow nearly circular orbits, HD 80606b's orbit is so elongated that its distance from its star fluctuates immensely, ranging from just a few million kilometers at its closest approach to a far more distant position. As a result of this extreme eccentricity, the temperatures on HD 80606b can swing drastically during its orbit. When the planet is near its star, it experiences intense heating, with surface temperatures soaring to as high as 1,700 degrees Celsius. This kind of heat is enough to vaporize many materials, creating a tumultuous atmosphere filled with hot gases and possibly even clouds of molten rock. This extreme heating phase is brief but powerful, likening it to an oven being turned up to maximum. Conversely, as the planet moves away from its star, it enters a phase of rapid cooling. This means that the temperature can drop significantly in a relatively short period, potentially allowing for the presence of different materials and atmospheric phenomena. These cycles of intense heat, followed by dramatic cooling, can lead to fascinating surface conditions, including variations in pressure and the possibility of forming clouds or storms in its atmosphere. Such unique characteristics contribute to the intriguing nature of HD 80606b and serve as a reminder of the remarkable diversity of worlds beyond our own. By studying planets with extreme orbital properties like HD 80606b, scientists can gain deeper insights into the mechanics of planetary atmospheres and the intricate dance between orbit and climate in the universe. As a celestial body gets closer to its star, the intense heat it experiences can profoundly affect its atmosphere, leading to significant changes in both composition and structure. This phenomenon is especially noticeable in planets that orbit their stars at close distances, where temperatures can soar to extreme levels. The rapid heating prompts an increase in thermal energy, which can lead to the evaporation of atmospheric gases. Such planets may lose lighter elements, such as hydrogen and helium, as their atmospheres become less stable under these conditions. When the temperature rises, various atmospheric processes accelerate. For example, the chemical reactions that form clouds can occur more rapidly, potentially leading to the formation of thick, noxious layers of gas. This can produce a greenhouse effect that traps heat, further intensifying temperatures and altering the atmospheric dynamics. In turn, this creates a cycle where the heat causes additional atmospheric loss, reinforcing the severity of conditions that might remind one of extreme environments found on Venus or Mercury. Additionally, rapid heating can also lead to winds reaching remarkable speeds, driven by the intense temperature gradients between the day and night sides of a planet. This creates extreme weather patterns, including storms that can be far more powerful than anything observed on Earth. Such dynamic interactions result in a continuously evolving atmosphere, showcasing how the intimate relationship between a star and its orbiting planets can lead to unique and sometimes hostile environments. Overall, the changes brought on by rapid heating as a planet approaches its star offer a fascinating glimpse into the challenges faced by celestial bodies. Whether these conditions could allow for habitability or render a planet utterly uninhabitable is a vital question in the field of exoplanet studies, sparking ongoing curiosity among scientists and enthusiasts alike. HD 80606b is an extraordinary planet located approximately 290 light-years away from Earth in the constellation Ursa Major. What makes this planet particularly fascinating is its highly eccentric orbit, which means it does not follow a perfect circular path around its star. Instead, HD 80606b swings close to its star at one point and drifts far away at another. This unique orbit leads to dramatic changes in its atmospheric conditions, which astronomers have closely monitored. To track and understand these orbit-induced changes, astronomers utilize telescopes equipped with sophisticated instruments capable of detecting subtle variations in light. They observe the planet's transition across the face of its star, a phenomenon known as a transit. During a transit, the planet blocks a fraction of the star's light, allowing scientists to infer information about its size, composition, and even temperature. The data gathered from these observations over time provide insights into how HD 80606b's atmosphere responds to its changing distance from the star. Additionally, astronomers use a method called radial velocity measurement. This technique involves monitoring the star's slight wobbles induced by gravitational interactions with the planet. As the planet orbits, it pulls on the star, causing it to move just enough to be detected. By assessing these wobbles, astronomers can calculate the planet's mass and further refine their understanding of its orbit. Through ongoing analysis, researchers have observed that as HD 80606b approaches its star, it experiences a spike in temperature, leading to dramatic shifts in its atmospheric composition. This knowledge not only enhances our understanding of this intriguing exoplanet, but also offers broader insights into how similar planets might behave throughout the galaxy. The study of HD 80606b serves as a testament to the incredible advances in astronomical techniques and our growing comprehension of planetary systems beyond our own. The study of tempestuous orbits, particularly those that are chaotic and unpredictable, offers profound insights into the complexities of gravitational dynamics and celestial mechanics. These orbits can occur in various systems, including those with multiple bodies, such as planets influencing each other's paths or satellites spiraling around massive planets. By observing and modeling these movements, scientists enhance their understanding of fundamental principles governing motion in space. One significant scientific value lies in the application of chaos theory. Many systems in the universe display chaotic behavior, where small changes in initial conditions can lead to vastly different outcomes. By studying these tumultuous orbits, researchers can witness chaos in action, helping them to decipher the underlying mechanisms that drive the order and disorder within celestial systems. This knowledge can also enhance predictions about the future behaviors of those bodies and their interactions. Furthermore, investigations into tempestuous orbits can shed light on the conditions necessary for planetary formation and stability. Through the motion of bodies in chaotic orbits, scientists can explore how a planet's position and the presence of nearby bodies contribute to its likelihood of developing a stable environment. This has implications for our understanding of exoplanets and the potential for habitability elsewhere in the universe. Lastly, these studies have practical applications in space exploration. By comprehending the influences that lead to chaotic orbits, engineers and scientists can plan more effective trajectories for spacecraft. This ensures that missions navigate complex gravitational fields efficiently, maximizing fuel utilization and optimizing routes for exploration. Ultimately, exploring the nuances of tempestuous orbits enriches our understanding of the universe while paving the way for advancements in space travel. HD 80606b is a fascinating exoplanet located about 190 light-years away from Earth, and it presents a unique opportunity for scientists to explore the intricacies of planetary systems beyond our own. This gas giant is classified as a hot Jupiter, meaning it orbits very close to its host star, resulting in extreme temperatures and atmospheric conditions. What sets HD 80606b apart is its highly eccentric orbit, which brings it much closer to its star at one point in its orbit, and then takes it far away on a long, elliptical path. This unusual behavior invites us to consider how such dynamics can affect the evolution of planetary systems. The dramatic temperature fluctuations that HD 80606b experiences provide valuable insights into the atmosphere of gas giants. During its periastron, the point in its orbit closest to the star, the planet can reach temperatures exceeding 1,000 degrees Celsius. This rapid heating creates powerful atmospheric winds and even violent storm systems. Observations of these atmospheric changes can help scientists better understand the broader behaviors and characteristics of gas giant planets. These insights can be applied to examine atmospheres on planets in various distance and temperature scenarios throughout the cosmos. Furthermore, the eccentricity of HD 80606b's orbit raises intriguing questions about the gravitational interactions within its system. Gravitational perturbations from nearby planets or other celestial bodies could play a crucial role in shaping the orbits of planets within a system. By studying HD 80606b, astronomers can gather clues about the formation and dynamical evolution of other planetary systems and how different factors might lead to similar orbital patterns in various galaxies. The processes at play in systems like HD 80606 provide a window into the potential diversity of planetary arrangements in the universe. Observing such extreme cases helps us build better models for understanding both our solar system and the multitude of diverse planetary systems that exist. Ultimately, as we delve deeper into the mysteries of planets like HD 80606b, we gain a clearer picture of how planetary systems evolve and the myriad of possibilities that await us in the expanse of space. Dramatic temperature variations within a single planetary year can have profound effects on the environment, climate, and even the potential for life on a planet. Such variations can lead to stark changes in weather patterns, impacting ecosystems significantly. For instance, if a planet experiences extreme fluctuations, it may cause rapid cycles of freezing and thawing, affecting vegetation and animal behavior. This shift can unravel food webs as species struggle to adapt to the changing conditions. Additionally, these temperature swings can lead to increased atmospheric instability. When warm air cells collide with cold air masses, it can result in violent storms, heavy rainfall, and sudden climate events. Such conditions challenge the natural balance of ecosystems, leading to shifts in habitat availability and species migration. In the worst-case scenarios, extinction rates may rise as organisms fail to adapt swiftly enough to their radically changing environments. On a planetary scale, severe temperature variation can alter geological processes as well. Melting glaciers, for instance, can contribute to rising sea levels, changing coastlines, and even reshaping river systems. This constant flux may also expose previously hidden geological features, impacting future geological studies and explorations. Ultimately, the potential outcomes of extreme temperature variations are a testament to the interconnectedness of planetary systems. The relationship between climate, geology, and biological life forms a complex web that sustains or disrupts the delicate balance needed for diverse ecosystems to thrive. Observing these dynamics can provide critical insights not only into our own planet's past, but also into the conditions that may exist on other worlds within our galaxy. The planet HD 80606b, situated about 188 light-years from Earth, offers a rare glimpse into the dynamics of extreme planetary climates. This gas giant orbits its star in a highly eccentric path, experiencing a dramatic shift in temperatures as it moves closer to and then farther away from the Sun. The unique nature of its orbit means that in just a short period, HD 80606b's temperatures can soar by hundreds of degrees, leading to rapid climatic changes. Simulations of this orbit allow scientists to investigate what might happen on other planets under similar eccentric orbits. By modeling the temperature fluctuations on HD 80606b, researchers can analyze how the planet's atmosphere reacts to such extreme temperature swings. These simulations reveal how atmospheric pressure, winds, and even cloud cover can change dramatically within a single orbital cycle. This is particularly relevant for understanding the potential climatic behavior of exoplanets, especially those that may be orbiting stars in similar patterns. Furthermore, these insights can educate us on potential climate shifts of Earth-like planets that are subject to intense energy forces from their stars. For instance, if an Earth-like planet were to experience an orbit as eccentric as HD 80606b's, scientists can hypothesize how that planet's atmosphere might behave. Would it maintain stable life-supporting conditions, or would rapid climate shifts hinder habitability? In broadening our comprehension of planetary atmospheres, simulations of HD 80606b serve as a vital tool. They allow us to not only understand the specific characteristics of this distant world, but also to apply that knowledge to the many planets we have yet to discover. By examining these extreme scenarios, we gain a clearer perspective on the potential for life and climates elsewhere in the universe. HD 80606b is a fascinating exoplanet that takes the concept of extreme orbits to a new level. Located about 190 light-years away in the constellation Ursa Major, this planet orbits its host star in an eccentric path, meaning it doesn't follow a perfect circular route. In fact, its orbit is highly elongated, resembling a squished ellipse. This unique arrangement results in dramatic variations in its distance from the star, leading to some incredible temperature swings. As HD 80606b draws close to its star, the temperatures skyrocket, reaching levels that can exceed 1,000 degrees Celsius. When it moves to the far end of its orbit, temperatures plummet dramatically, potentially dropping to much colder levels. This remarkable ability to swing between extreme heat and relative coolness invites interesting questions about adaptation and survival. It challenges our understanding of how life might thrive under such fluctuating conditions. Imagining extraterrestrial colonies on such an exotic world involves contemplating advanced technology and bioengineering. Could inhabitants develop protective habitats capable of withstanding intense heat during close proximity to the star? Perhaps they could harness energy more efficiently during the cooler periods when they are farther away. This vision relies on a profound understanding of materials and energy systems. hinting at a future where humanity can transcend its earthly limitations and inhabit harsh environments. The existence of HD 80606b ignites a thought-provoking discussion about the potential for life elsewhere beyond our planet. It compels us to rethink what makes a planet habitable. While it's easy to picture colonies flourishing in Earth-like conditions, HD 80606b's extreme environment encourages us to expand our imagination. It reminds us that in the vastness of the universe, life might find a way to adapt and thrive in conditions we find inhospitable, making the cosmos a more intriguing place. The discovery of the exoplanet HD 80606b has significantly challenged our understanding of planetary motion and the models that describe it. This planet, located about 205 light-years away in the constellation Ursa Major, is highly eccentric, meaning its orbit around its star is elongated rather than circular. At its closest approach, or periapsis, HD 80606b experiences dramatic shifts in temperature and atmospheric pressure, a scenario that has forced astronomers to re-evaluate the traditional models that typically assume more stable, circular orbits for most planets. In particular, HD 80606b's orbit takes it from a distance of 5 astronomical units to just under 1 astronomical unit from its star, a staggering difference. As a result, it can reach temperatures approaching 1000 degrees Celsius during its close approach, only to drop drastically when it moves farther away. This level of thermal variability was not anticipated in existing models, which usually explained planetary atmospheres based on stable distances and temperatures. The extreme nature of HD 80606b's orbit suggests that some planets may not fit neatly into established categories, leading to a rethinking of how we classify exoplanets based on their orbits and climates. Moreover, the planet's intricate interactions with its star raise important questions about orbital dynamics. Unlike many planets that maintain a relatively consistent distance from their stars, the wild fluctuations seen with HD 80606b hint at a complex gravitational influence, possibly from other celestial bodies in the system. This phenomenon has broadened our inquiry into how multi-planet systems might interact and how those interactions can result in unexpected orbital shapes. By examining HD 80606b, scientists are not only gaining insights into the diverse environments of exoplanets, but are also prompted to reconsider the frameworks we use to understand planetary formation and motion. This landmark discovery encourages a greater appreciation for the intricate dance of celestial bodies and underscores the dynamic nature of the universe, illustrating that our models must evolve in accordance with the realities observed in space.